Hello, everyone, and welcome. It is Wednesday, and it is a special day today. We are continuing to do things here that no one else is doing, and it's really fun to lead the pack and lead the crew. The Knowledge Bolide Crew is strong, and we never miss. So, we are today doing something that is just really super exciting. When I went to Tucson this year, we went to, well, hold on, do I have this screen? There we go. Okay, we're doing the classification process. This is another episode of From the Lab starring Daniel Sheikh. So Daniel is our classifier to the stars we've been working with for years. And when I went to Tucson, we all put in on a group stone. We bought the stone, we got it sliced up, and now we're getting it classified together. So everyone here is actually going to be part of that process of the classification process. We're going to be watching it done live. We're going to be asking questions about the process, and we're all going to be participating. Anyone who's on my list over here has been asked to participate and pick a location of the thin section where we're going to be taking readings from for Daniel. So I don't think this has ever been done before, and we're going to try not to edit this video. It's going to be put up in as most raw form as possible, so I hope you enjoy. It should be about 3 hours, so settle back. First off, this is the rock we purchased from Mohammed Hmani. Mohammed is a friend of ours. I see him in Tucson every year. I met him in. If you look at my channel and you see the video from Quartzsite that I'm shopping for meteorites, I'm shopping at Mohammed's place, and we spend the afternoon together. He made the video. Not meaning he made the cut, but he made the video successful. So this is Mohammed and I in Tucson this year in 2025 purchasing said stone. Now, just to be clear, we did do 2 of these. We had such good engagement and excitement in the first one, this one right here, that we actually had other people, our Patreons, ask if they can get involved in it. So this is a second rock we purchased for our Patreons and some others to excuse me, to participate in. This is not the stone we are doing today. This is the stone we are doing today. Number 1. We're going to find out exactly what it is. We all have our ideas, and think everyone live is dropping in the chat exactly what they think. But this is exciting, guys. As I said, you're seeing the sausage made. So this is super exciting. I'm really happy. Oh, now I can actually show my rock off. So this is the one that we're doing today. Everyone here who's live can drop their ideas in the chat as soon as possible, or as late as possible if you want to cheat, or if you want to gain as much scientific information first before you make your suggestion, your classification guess. But that is the rock we are doing right here, classification number 1. And here's some beautiful, sexy pictures of it. Some of these we can vote on these guys, so we'll have to make this a continued project. Which of these should we send to Daniel to submit with the classification as the main mass picture? Because there are no other pictures of the main mass except for the ones I took and I'm sharing with you guys. It's been cut up, dissected, and polished, and is no more. But it's beautiful. Still has some good fusion crust for its age. So are you guys guessing about your weathering grade right now? What about your shock values? This thing does show a good amount of shock through it. You see a huge shock vein here and one coming through here. So I forget, babe, do you know what the total weight on this was? Greg Shano slag. I don't ever look at chat. Look at chat one time and I see slag.
It was 9,580 grams.
9,500, so 9.5 kilos of awesomeness. Definitely see contraction cracks in the fusion crust. That's even on an aged meteorite.
These were the first pictures I took with my new camera, my new phone
Oh,
camera.
nice. It looks really good. It
You can
captures
actually zoom in and it's not pixelated
the
anymore.
color of this picture is true to life. This is exactly what the rock looks like. Wow. Beautiful. Look at that big old shock vein. So this we also have to, as a group, as part of the classification, we have to write a descriptive narrative, if you will, of what the rock looked like before it was cut. So the rock resembles this, it was color of that, angular of this, remnant fusion crust here, whatever, you know. So as a group, we're going to be continuing to work on that. And Daniel's going to provide us with the form where we can send that information. So we're going to be working on the whole classification together, guys.
Well, people are coming up with some really specific classification guesses.
Good. They should. They have
It's
to.
awesome.
We know our stuff. All right. So, you know, we stand on the shoulders of others to achieve the greatness that we have. And wow, the chat is just blown. I love it. So this is a little homage to our partners. So we appreciate, first off, Craig's Lehman at Minnesota Meteorites did all the cutting and polishing, and he is the absolute rock star of cutting and polishing as far as and restoring meteorites. So he did all of the cutting and polishing on this, and he did a fantastic job. Mohammed Hmani and Mohammed Ismaili Mohammed. Both are our suppliers for these stones, friends of the Knowledge Bolide, friends of many of us who go to Tucson. And, you know, when you find the stone and it's a kilo over your budget and they make it happen, those are the guys we need to thank as well. So they're definitely our partners in this as well. Here's Craig teaching a school. I'm hoping that this kid right here is really interested in a regmaglyph down here and he's not falling asleep. Let's just assume he's super interested. Like that's the most focused kid in the room right now. Our thin sections were done by Spectrum Petrographics. These were, I think this was Daniel Sheikh's recommendation. And thin section preparation and analytical petrographic services, Vancouver, Washington.
Those are just the services that they offer.
Oh,
Also, one last thing before
gotcha.
you jump in with Daniel, if you go to your instant messenger and look at the last message you sent to Daniel, which was me, is a picture of the thin section with all of the plot points on it.
Oh,
But we're not gonna,
sweet.
that's not part of the intro. We're gonna do that later when Daniel's ready.
Oh, nice. Good. Okay. Yeah, that I'll explain that later. This is it right here. So this is the picture of the thin section that was made for the classification. Some of the other members of our classification group chose to buy a thin section for themselves. But this is the actual thin section that Daniel's going to be working on tonight as far as the classification process goes. So again, this is something I've never seen done before. We got together and we said, hey, look, here is the, I don't know if I can zoom. No, I can't. Here is the thin section that he needs to collect data points off of for his classification process. Why don't we as a crew think of them and point them out together? So we've been looking at this thin section, picking out points of interest. I have two points of interest picked out, and I want to see if they're the same material. So I'm hoping that other people were able to pick some interesting places for gathering information, and it helps really solidify the classification process. And that is the final slide. Awesome.
I think would be fun is everybody's taking guesses right now on the classification. When we're all done with the rental and we're about to wrap up, I'm going to send a poll out and ask for everybody's official guess and see if it's the same. And we'll see what the consensus is. And then obviously Daniel has the correct answer because he'll know.
Nice. Um, did you send me a message?
It's
Can you
a message you sent it to Daniel on Messenger, but
Oh,
I can.
did you?
Would you like me to
Gotcha.
send it to you a different way?
Nope, I got it. Okay. Yeah, let me share this with the crew.
Someone's asking for the NWA number. It's not classified yet. That's what we're doing tonight. And now it's not slag, Greg.
Okay, so this is the thin section. Hopefully you guys can see that. This is the thin section that has been shared with the crew, and everyone's picked a point of interest. So we can see a few people got some points of melt. Looks like a few melts. Most people are around the melt. That's really odd. I chose, oh, only one of mine is here. But I think this is mine right here. I wanted to see this material. And was it right here, I think? I wanted to see if that was the same material. But yeah, you can see that there's a lot of material in here, a lot of real estate to pick from. And we wanted to give Daniel a good, so Daniel has this now. Daniel's in the building. I don't know if he's all logged into all his devices or not, but we're going to try to get as many views into this as possible so you can see him working, see some screens, see some instruments, all that kind of stuff. So,
what's going on, everyone? Can everyone hear me?
Hey, bud. Yeah, we can.
Awesome. Okay, so I think I've maybe figured out a way to make this work. So
nice.
Yeah.
Welcome,
got,
buddy. We are so
awesome.
excited to do this with you, man.
Okay, so can everyone see me?
Absolutely.
All right, perfect. Okay, so right now I'm in the, so what I'll do is let me turn this camera around. Okay, so this is essentially where, let me put that there. Okay, so this is where all the SEM work is done, all the classification work is done. This is we call it a Sigma Zeiss variable pressure field emission gun scanning electron microscope. It's hooked up with different detectors depending on what sort of application you're trying to do. So what we're going to be using is this one right here. This is called a Ultimax SDD EDS detector. Basically, this is where we get the chemical compositions of our mineral phases from. The other detector we're using, you can't see it in here, but it's beneath what's called this area called the column, and it's called a backscattered electron detector. And that's what we'll be using to get images of our sample. So the combination of that detector and that detector will give us all the information we need to do the classification. And so just very briefly, I'm just going to explain a bit about what electron microscopy is and why we use it to classify meteorites. So essentially, what you're seeing here are two thin sections. The one on the left, this is the group classification. You can see it kind of looks like that picture I sent, and it's on a mounted stage. And what I'm going to do is I'm going to put this stage into this chamber. And once it's in the chamber, it's going to be set up. And then essentially there's a source that produces electrons via a process called thermoionic emission. These electrons will travel down this column and they're accelerated. They'll interact with atoms in our sample. And depending on the type of interactions we get, we can form X-rays, which we pick up here and get chemical composition, or these electrons are essentially what we call bounced back elastically, and we pick them up here to produce images. And so that's essentially all there is to it. We're gonna go to as many sites as possible, get as many images as we can, get a lot of data points. We can make maps where we can see different elements mapped to a color, and we'll classify the sample. So that's really all there is to it. So what I'm going to do now is I'm going to take this is copper tape, and what I need to do is I need to make a conductive surface. So I'm going to put 2 layers of copper tape, one on the top, one on the bottom. And then once that's done, I'm going to use this system right here to vent the chamber, because right now we're at essentially near high vacuum status. So I'm going to vent the chamber back to air pressure. Then I'm going to put this in, and then I'm going to pump it back down to high vacuum, and then we'll get started on the analysis. So if anyone has any questions while I'm getting this set up or putting in the instrument, now would be a great time.
Sweet.
And I'll turn my video off while I'm currently taping this.
If anyone has any questions about this, by all means, open mic night right now. Now.
Okay, I'll bite. How much
There
does
we
that
go.
machine cost anyway?
How much does it cost? Great question. So it depends on the model. So I believe, including all the detectors, so it's probably between, I'd say, maybe 500 to maybe 700. 100,000, somewhere there. SEMs in general range depending on what kind of model you're looking for. So desktop SEMs are the ones you can sort of like have on a table, and those ones cost anywhere from, you know, I'd probably say 60 to maybe 150 to 200,000. This is a standard, you know, regular size SEM, so probably 300, 400K, and then the detectors are usually about 100, 150 each. So yeah, I'd probably say it's a little more than you know, a portable XRF detector. I'll say that, yeah.
All right. Thank you, Daniel. Thank you.
Awesome. Appreciate it. Ken, welcome, man.
Yeah. Yeah.
Yeah, I was going to ask Daniel, is he protected or shielded from any radiation while this instrument is doing its work?
Great question. I would hope so. Otherwise, I wouldn't be here very long. No, there's definitely a lot of protection from where the X-ray source is versus where I am. So thankfully, there isn't any risk of any, you know, radiative damage, at least on my end.
Awesome. Thanks, Art. Pinsky.
Yeah, this may be a silly question because I remember at the Natural History Museum at the Mineral Hall, they have an electron microscope, but they have to coat whatever they're going to image with gold. Is that a different type of thing than what you're doing? I'm just a little confused on that.
Yeah, that's a great question. So yeah, one of the big things whenever you're looking at things like silicates or when you're looking at samples under the scanning electron microscope is you need to have a conductive surface. So it needs to be flat, it needs to be polished, and it needs to be electron conductive. Otherwise, you can get things like what are called charging, where electrons build up on your sample, and they can undergo a process called sputtering, where they can essentially fly off and hit your detectors and cause a very expensive bill. So in order to get to see your sample effectively, not cause charging issues, you have to coat your sample. There are some people who coat their sample with gold, but for this purpose, we coat our samples in a layer of graphite. So whenever you hear the term carbon coating that's used, that's essentially what we do. So let me see if I can just very briefly turn my video on.
Yeah, and just so you know, Daniel, feel free to engage in conversation or focus on your classification as you absolutely need to.
Sure.
We want to make sure that, but I'm super interested in the carbon coating because I've had the same question myself.
So what we do is you put your thin section right in there, and you have these two graphite rods, one you sharpen, one you keep flat, and you keep them together, and they're held together with this tension. And then what you do is essentially you close this chamber, you pump it down to high vacuum, and you essentially induce a current that runs through it and vaporizes the graphite. The graphite gets deposited on top of your sample, and because it's under vacuum, hopefully it goes out very smooth and flat, and then essentially coats the very surface of our sample. So we're talking about nanometer thicknesses of this graphite being on our thin section. So what you end up seeing is if I show this now, essentially there's a very thin layer of graphite that's on top of here. It's really hard to see unless you see a thin section that's not coated. But if you go on my channel and you check out my classification vlog 1, you'll see that I show using this carbon coater. So you can sort of see it a little more. But essentially you have to coat all of our thin sections before they go in here. So that's step 1. Step 2 is now that we have it all set up, we have carbon coated thin sections. We have our copper tape that's on top and on the bottom. This is ready to go. So now essentially I go to the SEM computer and I hit vent. And now we're essentially venting the chamber and we're going back up to air pressure. This will take probably a minute or two, probably 2 to 3 minutes. And then once it's back up to there, this is pumping nitrogen gas in to bring this pressure up. Then we can put our sample in, and then we can get started.
Wow, very cool. Sue?
Yeah, Dr. Ralph put something in the chat, so I just wanted to make sure that Daniel heard it, and I wanted to congratulate him too. Congratulations to Daniel for his recent award in Perth.
Oh, thank you.
And then I have a quick question. So I just wanted to check the accuracy of something I put in the chat. Would you say that like the rental of this like super expensive like equipment does that make up a big chunk of the like what it costs to get something classified, or are there like other things that outweigh that?
Yeah, this is definitely one of the factors because you have to request time to use the instrument. So obviously, there is a fee associated with using this. There's also a fee associated with making thin sections, depending on who you use and the service. So I work with Spectrum Petrographics, and they have a 2 months thin section making process that they charge for a cost. All their prices are online on their website. They have faster turnaround times, but then the price is higher. But yeah, it's a mix of using the instrument for beam time and thin section cost. Those are essentially what drive the classification price primarily.
Gotcha. Thank you. We just got those thin sections in the mail the other day. Very exciting.
So we have everyone dropping. Oh yeah, Scott McGregor says even more when you have the classification costs are even more extreme when you have oxygen isotopes needed or done. So
Daniel, when are those needed? Is that just for like lunars and Martians and like carbonaceous, or is it you know, case by case basis?
So it's really a case by case basis. One of the things that really drives oxygen isotopes is due to the fact that when you have something that doesn't quite fit in a specific meteorite group in a certain way, or you have a sample that doesn't fit with any of the existing groups. So a great example of that is this recent ungrouped A chondrite that I worked on. It's called Northwest Africa 16111. So it has, if you look on the MEPL page for it, you'll see it has these very unusual mineral chemistry to it. That's kind of similar to the Uralite meteorites, but a little bit different. So I wanted to get oxygen to see if they were related to Uralites. So in this case, it would be called an anomalous Uralite if it was classified, or if it's just some completely different meteorite group that we haven't sampled, in which case it'd be called an ungrouped A chondrite. So I had the oxygen work with someone who does the work, and it came out that it was a little bit different than most Uralites. So hence we came up with the ungrouped A chondrite term.
Fantastic. Before we get back to Daniel, I do want to say that Daniel has a YouTube channel everyone should be subscribing to. His literally, it was served up to me before I walked in here for the live. He has a video that he just plugged, the classifying a meteorite vlog 1. It has under 1,000 views. Come on, man, that's ridiculous. Everyone needs to go and watch that. If you're into meteorites and meteorite science, subscribe to his channel, watch his stuff. He has been so great about sharing his time and information with us. And like this entire video is not going behind any members paywall or whatever. We're putting it out there in public because that's one thing that Daniel has always been an advocate about with our channel. So back to you.
Yeah, thanks, Topher. Yeah, really what I'm trying to get out with classification is, again, make it more something, that's open, available to the public, something everyone could see. And obviously something that is also free to the public to see, to have access to. So any sort of, whether it be videos, vlogs, whether it be an article online at some point or a book online at some point in the future. I mean, it would be something I would like to be available to everyone, and not something you'd have to pay for, just so more people can get involved. Because one thing that I've been noticing is that there's not many people who classify meteorites. And so trying to bring people into it is, you either have to read a lot of papers or you have to work at a lab that does it. There's no real like in between, but having some sort of guide, or at least some sort of entry point that's easier for someone who may have experience using a scanning electron microscope. Maybe they're doing a research project for their undergrad degree in geology, something along those lines, or even as a high school student, working with a professor at a university who is interested in meteorites. I want to make it accessible, at that level.
Yep.
That's awesome.
Yeah.
Okay. All right. I think
Please.
I've got it. If for some reason this falls or something happens, please let me know.
Yep.
All right, so I'm going to try to work around it. So you're going to see my hands here. So I can't show the controls and the screen, but at least you'll see the screen. So, okay, so what you're seeing here, this is the stage. or thin sections on top. And what I'm doing is I'm controlling what's called the Z. So the Z movement means we're moving up. This is the bottom of the SEM column. It's called the pole piece. And these are where our electrons are essentially coming out. And then here's where they're interacting with our sample. So what I'm doing now is I'm just making sure I'm lined up correctly, which I am. You can see it says right here, vacuum. There's a check. That means I'm at high vac. So that means I'm all set. And so the next thing I need to do now is I need to bring in my detectors. So what I'm going to do now is I'm first going to bring in my X-ray detector or my EDS detector. You'll see it coming on the screen in a bit. Yep, there it is. Takes about 15, 20 seconds. And then while that's going, I am going to insert the backscatter electron detector. So I have to get up for this, so I'll be right back.
This is badass, man. Yeah. Pat, I am looking at your monitor every 10 minutes. If you have a cardiac event, we will alert authorities. Just
Okay, all right. So we're all set. Okay, so now here's where everything starts. So this EHT, I don't know if anyone can everyone see my mouse moving
Yep.
around? Okay. So when I click this, now we're turning on the electron gun. So now it's starting up. So hopefully we have no problems. Make sure everything is set up over here. Okay, so you're not going to see everything perfectly right away. You're going to see a screen like this, so we have to do a couple things. First thing I always do is I have to change this working distance. So what I'm doing is I'm setting it to 8.5. What this is called an analytical working distance, meaning that our thin section will be exactly a certain distance away from the top of where the pole piece is and a certain distance away from our other detectors. So what that means is that I'm set up for quantitative analysis mode, if that makes sense. All right, so we're starting to see some stuff come into play here. All right, let me do this. Check something really quick. Okay, let's see here. Now I just have to check some current. Okay, that's good, that's good. Temperature size is good. Let's see, we're good there. All right, we can keep it at that for now, that's fine. 4.
in case I didn't say it already, from the entire group, the Knowledge Bolide Crew thanks you, Daniel, for your time and doing this for us today. Like, you're not charging any extra for the classification. You're literally taking your time to slow roll this and give us all this education just out of the goodness of your heart. So
No
thank you very
problem.
much.
Yeah, no problem. Okay, so we're on the sample and you can see it's a little blurry. You can see the colors are a little bad. So what I need to do is I need to get into focus. So I'm zooming into about 1,000 magnification. So what that means is that this scale bar says anything in here is 10 microns. So we're seeing pretty small stuff already. But what I have to do is I have to make sure I get in focus. So what I'm going to do is I have to do that first. All right, so I got to go the other way. Okay, give it a second.
Wow.
All right, so what the mode I'm in now is called secondary electron mode. What this means is I'm using a different detector from the backscatter detector, but this is looking at, these can look at things like surface topography. This is what we use to focus our sample. And then once we're good on here, then we're going to move to the other detectors. So let me find a very small point on here. Let me see something really quick. Okay, so let me just zoom in. Actually, let me zoom out. All right, let me just check something really quick. I'm just going to switch to the other detector. I just want to make sure that it's working. Auto level. Okay, all right, cool. So that is working. All right, let me go. Okay, so let me go back to this detector. Just lower that. All right. So, so we're on the sample. So we don't know where we are, but first what I have to do now is I have to do what's called a beam calibration. So that will essentially set us up for quantitative analysis. So if I can, so what I'm doing now is I need to navigate to the copper tape that I had earlier. So I'm just moving throughout the sample. Okay, so it's going to be a little bright, or this. Okay, let me find a clean spot. So I'm trying to find a clean spot on this copper tape. So somewhere here. And what I'm doing is I'm just getting it in focus again. Nope, other way. Okay, all right, so now it's in focus. So now what I'm gonna do is I'm gonna shift over to the computer. So am I good to share my screen on that?
Absolutely.
Okay, so let me do that real quick. So what I'm on, this is a program called Aztec. This is essentially where we do all of the data collection, all of the data processing. And this is essentially what I use to, take images and what I use to collect data from your sample. Before we start, I have to do what's called a beam measurement on the copper tape. And what that's doing again is it's essentially allowing me to get quantitative spots of your sample. So right now I'm just running a calibration right now. And once that's complete and everything is good, then I will go back to the other screen and we will begin navigating.
So this is a focusing and calibration, basically, process or practice.
Yeah, so one of the things that we have to do when getting quantitative measurements is if you're trying to get, for example, you might see data reported in things like weight percent oxides, like you might see elements like silicon as like SiO2 or magnesium as MgO. Well, with this software, the beam calibration, what it lets us do is we can essentially get a better measurement of all of those oxides, and we can obtain what are called unnormalized totals, which means that we can look for things like whether we have the presence of hydrous minerals or whether we have anhydrous minerals. And it's also very good to get this beam measurement because this essentially lets us check to make sure that during the analysis that we had a consistent, what we call current. So really all we're doing is we're just taking this measurement now so that when we get data of our samples later, we can check our samples to see their, how the data quality is and whether or not there's been some drift in our beam current over time.
Okay.
So it's a little bit of a complex
that
subject.
and a benchmarking actually too.
Yeah. And so what I'm doing now is I'm just going to map mode and I'm just making sure everything is good. Okay, so now I'm going to stop the share and I'll go back to the other video. Okay. All right, so basically we're all good to go. Our beam measurement is good. So now we'll go back into the sample. And before we go to the, the assigned sites that everyone picked, I'm just gonna go to a random location. So let me go to, okay, let's go to this nice little Condrule right here. And then I'm just gonna, actually, let me go to somewhere where I have a bunch of different phases. So let me go here. And so what I'm doing now is I'm going to turn on the backscatter electron detector. Actually, before that, let me just check something. Okay, good. Just want to make sure the sample isn't running into the whole piece. All right. And then let me do this, auto level. Okay, let me try to now change these settings. Let's put that up. Let's get that to maybe here. Let me try 70. All right, something like this. So I'm just adjusting brightness contrast settings to try to get, so what I'm doing is you'll see all these different grayscale colors here. Essentially, these correspond to something that's called the Z value of what you're looking at. So The whole point of using the backscatter electron detector is because phases in your sample, so example, if you have metal or troilite, those contain elements that have relatively high atomic numbers like iron, nickel, cobalt. So your average Z value or proton value is going to be relatively high. The higher your average Z value, the brighter the intensity. So your metal and troilite are going to be these bright things here. And the darker your average Z value are going to be things like your silicate phases, like olivine, pyroxene, feldspar. So this image essentially lets you compare based off of the relative grayscales, what mineral phase you're looking at. But it's not perfect because you can have mineral phases that have either very similar grayscale values, so you can't tell them apart, or you can have one mineral phase that's zoned, in which case its grayscale value will vary. So for then we have to do something by getting chemical maps. But for now, at least, we are on the sample. And so let me just navigate around, just check to make
Now
sure
it really
we're
looks
good.
thing.
Yeah, so now everything seems to be in focus. I'm just going to see. So now I'm going to go to a higher scan speed. So now it's going to, so essentially what's going on is the electron beam is racing across your sample and it's generating this image. When you increase your scan speed, you're slowing down the racer time. That's why you see that little bar navigating. So if I move at a high scan speed, you're going to see it kind of like shifts like that. But then if I go to a lower scan speed, it goes a lot faster, but then the quality is worse. So when I'm navigating around through the sample, I go at a low scan speed, but then when I find an area of interest, I then increase it to high scan speed.
Very cool.
Yeah. Okay, so
Wow.
we're on the sample. It seems to be good. I can sort of see the phases. I'm going to just briefly tell you what each of these colors likely corresponds to, since I think I know what the sample is already, but these bright phases are going to be either metal or troilite. This very dark phase is most likely going to be either plagioclase feldspar, or it's going to be Condrule mesostasis glass. It's one of those two things. And this intermediate gray that you see everywhere, the lighter intermediate gray is likely olivine, and the darker gray is likely low calcium pyroxene. We may have some other phases in here. We'll find out, but essentially keep track of just these colors as we go through the sample. Okay, so now that we're all set, all right, where should we start?
I'm gonna pick up mine first, and then we'll go to Art.
Sure.
Mine is at like 2 across, 9 down.
Okay, so you're the red spot.
Yeah, that little area
Okay.
there. And if you look at like 2.5 down, around 3.5, like right around there. I wanted to see if that was kind of like the same material, but I definitely
Okay.
want the red one tested for me.
All right, so let's get there first. So let me do, let's see, let's do the, okay, let me hit that. So I'm going to the bottom left and I'm sort of moving up. And let me see if I can spot that. So usually what I do to try to identify spots from the thin section image to the scan electron microscope is I look for features that are noticeable. So metal is going to appear like essentially dark. So if I can see metal grains that have the shape that match what I'm looking at here, I kind of know I'm in the spot. Sometimes if there's a chondrule and I see like big silicates, I can use that as a way. So I'll try my best and we'll see if we can spot it. I might already be on it here, but let me just see if I can find that metal. Let's see.
I can imagine you can get lost on a slide, man.
Oh yeah, no, it's when you have large thin sections, it's very easy to get lost on these
Yeah.
sorts of things. Okay, let's see. You try using a, let's see. Okay, so I know where I'm at up here, so I already passed it. So I'm moving down. Okay, there's a metal grain there. And then if I move down further, we should be passing a vein, perhaps. Okay, no, okay, so there's another grain there. Then if I keep going down, okay, there's this. And then it should be right here, which I think is correct because that kind of matches up with that. And let me just check something real quick. Yeah, so this is that there, and then, okay, we're right in, here we go. Okay, so we're right in here. So this is, looks like some very large object.
Yeah.
Could be a chondrule, could of course be some other kind of inclusion, but we can definitely get some points. So, all right, so what I need to do is I could do one of two things. Sometimes I do what are called context images, where I take them at very zoomed out magnifications like this. But then if I'm trying to get chemical data, I have to be zoomed in at least 250 to 300 times to get good data. So what I could do is I can do something like this. So I'm going to first take a context shot so that we know where we are. For that, let me just get in focus real quick. Let's keep that. Okay. So I'm doing what's called a reduced screen zoom in. So the raster is only going on this spot, not the whole screen. So it's much easier to do focusing work versus if you had to do the whole thing, it would go very slow. All right, so we got that. So let me just make sure that we're at a good enough brightness. Maybe something like that. Okay, so now what I'm going to do is I'm going to transfer over to the other computer screen, and we're going to see exactly how we can get data from this. Okay, so let me just share the screen now. So so basically there are different tools you can use. We're first going to take a map, and then we're going to go do some points. But first, let's just take a context image. So I hit start. And so now what it's doing is it's taking what was on the SEM screen, and now it's putting it on this screen. And it's going to be in a little better resolution, so it's going to look a little more crisp. And so at the current settings I have, it's roughly about 80 seconds for each of these images to load. And then what I'll do is I'm going to call this, let's see, so I'll call this site 1 context, but what I'll do is I'm going to put your name, Topher, here, so that way each of the sites that everyone has, I can take pictures of, and then I could share all these. So if everyone wants to have actual images, of the sites I went to and navigated, we can have that also. So I know whose site is whose. So I'll do that.
That's awesome. Yes.
And let me do this also, red dots. Okay, there we go. So we'll wait for that to load. So a lot of time really on this instrument. Once you've already got everything calibrated, and then you're started, and you're moving around and locating, you're kind of just waiting. So this is kind of where that waiting thing is now. You're waiting for the image, and then so the image is about to end. And so now what I'll do is I'm going to take a chemical map. So now this is going to go to this tab called Acquire Map Data. And what I'm doing now is essentially the X-ray detector is now essentially picking up X-rays from this area of the sample. So what you're seeing here. And basically each of these elements corresponds to a certain color. And so if you have a lot of, for example, magnesium in a certain spot, it's going to appear very green. If you have a lot of iron, it's going to appear this shade of blue. If you have a lot of silicon, it's going to be this shade of pink. And so different minerals based off of these combinations will have different colors. Now, different people use different, elements, colors, schemes. Some people just use what are called RGB maps, where they have one element red, one green, one blue. We have a bit more of a complicated setup here. I'm using Alex and Melinda's setup that they use for chondrites. It's actually, I think it's the best way to capture all of the different minerals here. So I'm using it. But essentially, once this image finishes loading, I'll show you what phase each of these colors corresponds to, so that you're also adjusted. But it's a lot easier to see colors than it is to see a grayscale image. So this really helps.
Yeah, Daniel, maybe I can just get a quick question in, because it's right on topic. I actually wrote it down, but when is color versus black and white used?
So I try to get chemical maps anytime I'm looking at a backscatter electron image, unless it's like, like if I'm zoomed in on this one little grain right here, like if I'm all the way zoomed in and I'm just seeing this window, it's going to be the same thing. But any sample I'm looking at for the first time, I always zoom out and do a context image and then run a chemical map, just so my eyes can see like, okay, there's a lot of magnesium here. These are probably olivine, pyroxene minerals. I can see a lot of this purple here, which I know is indicative of things like feldspars. This yellow here is a mixture of the sulfur and the iron, giving me a sulfide. So this is like a troilite. I see this blue right here. This means there's a lot of iron, maybe a little bit of nickel in here. So this is like metal. And then this red here has some calcium in here, since it's got calcium is red. So this is probably a high calcium pyroxene. Whereas this more dull green is a low calcium pyroxene. And this bright green is a olivine. So this is kind of like what I use. Or sometimes you see this little pink thing. This has a lot of chromium. This is a chromite, another mineral you can find in ordinary chondrites. So anytime I look at a sample, doesn't matter whether it's a meteorite or terrestrial rock, I run a map. I want to just see like what the different phases are, and then I get points of each of them. So then it's like I know where to take spots. So that'll be the next thing we'll do, but we have to zoom in for that. So from this map, Topher, do you have any preference whether we go to the top right, bottom left? Is there any preference?
I actually have a pixel picked out.
All right. Okay. Where do you want to go?
If you go just south of dead center, there's a dark green square. Ba-boom.
Right here?
What is that?
Okay. We'll get there. So what I'm going to do now is all right. So I'm going to stay shared on this, but I'm going to make a new site. And it's going to be site 1 zoomed. And so I'm on the other computer. Let me just quickly zoom in on that and then get the image, and then you'll see it pop up on this computer screen. So just give me 1 second.
Yep.
I'm going to center in on that area, and I'm going to go to, maybe something like this. So 350 magnification. And then,
when it fits your narrative, if you can tell us how limited or how small of a grain or sample area.
Sure. So we can, I could go to things that are sub-micron in size. So things that, you can even, some people use this to look at things that are tens of nanometers in size, depending on the application. Fortunately for like geological applications, we're really concerned with things on a micron or higher scale. So like, here's the scale bar. So this is 250 microns. So 4 of these is a millimeter. And then obviously 10 millimeters is a centimeter, and so forth. So we're looking at pretty small objects.
40 of these is a scale cube.
Essentially a millimeter scale cube. Yeah.
Wow.
Yeah.
Wow.
So I've zoomed in on that area you've selected. And again, what happens is it has to take the image again, and then I can run a map again, and it'll be more zoomed in. So I'll take another map. And then after we take another map, I can then do chemical spots, and we can find out what everything is here. So, but yes, I will say that you see how it does look like a covering. I will say that you can get surface contamination on top of certain areas in your sample. And I think that's what's going on here, but who knows? It could be a mineral phase. So we'll find out shortly.
Okay.
All right, so now I will fire another map. And the cool thing about this software I'm using, Aztec, is every time you take a chemical map, it saves all of the chemical data stored in each of these pixels. So what that means is you can go back into the software and then, say like, what is the composition of this thing? Or what is the composition of this thing? And this is after you've already gotten the data. So like, let's say I forget to get a point or something like that. I can then go back in and like get a composition without needing to actually go on the instrument. But it isn't as nearly as accurate as if I was doing it in live time. So I always try to get as many points as I can while I'm on the instrument, because the quality will be a lot better since I'll be getting more what we call higher count rates. So this is what this screen you're seeing here is essentially saying. So when I start getting some spots, you'll start to see what I'm talking about.
How many collection points are needed, and how many do you go for in chondrites?
Depends always on the sample. So
Gotcha.
if it's a L6 with very few chondrules and it's unbrecciated, well, I mean they're all brecciated, but if it's an L6 and it's equilibrated, meaning that the composition of the olivine and the pyroxene are essentially the same, no matter where you navigate to in the sample, I try to stick to at least 10 to 15, if not closer to 20. If it's unequilibrated, like a type 3, like all of the type 3s that Pat has sent me, that requires a lot more time. I have to navigate to a lot of different chondrules and then get data. So it depends on the sample. If it's a lunar, I look at
Yeah.
all these different clasts. So it depends.
Yeah, fantastic. I'll also put the question to you, Daniel. When you saw this thin section, was there any spot that you were like, "Oh, that's pretty interesting. I hope someone picks that"? Because if not, that's your spot.
I mean, what I did was so obviously there were some visible shock melt veins that I know Vince, I don't know if Vince is here, but
Yeah.
he's very interested in those. He studies them for his master's research. And so whenever he talks about shock melt veins and all the cool high pressure mineral phases he finds in there, I always try to look in there myself just to see if I could find something interesting. So I think some people have selected some areas in those shock melt veins. So
Yeah.
to me,
Good.
that's a pretty cool spot already.
Nice.
Yeah. Okay, so the map just finished collecting. So now we're going to go into actually collecting spots. All right, so let me make sure I'm good. Okay, so what I have here is essentially I'm going to be making these small rectangles, and I can zoom in anywhere, collect rectangles, and it's going to be picking up X-rays from that specific spot and basically giving me the chemical data I need from my sample. So what I use to navigate is, it might be a little tricky here, but I'm gonna, if this looks a little complicated, I'll just use one image, but I normally use the grayscale image, but I use the chemical map as a guide for where to get spots. So,
Okay.
so Topher, you said you were interested in this spot right here. Is that correct?
Yep.
Okay.
Yeah,
So
it looked unique.
okay. So what I'll do is I'm going to get a spot in this area, and then I'm going to get a spot right outside of it. So we'll see if it's the same mineral that maybe has surface contamination or maybe a different mineral. All right. So the key thing is when you're getting spots, you have to be careful of two different things. You don't want to get spots over cracks. That's number one. And you don't want to get spots over a combination of different mineral phases, because then you're essentially just getting the mix of the two. You're not getting a pure mineral composition, both of which are detrimental to getting good data. So you always got to make sure. What I do is I use these cracks to like find areas that are like clean, and I take rectangles. And the final thing you have to note is what's called the interaction volume. So whenever I take a rectangle, essentially if I'm at least within 1 micron, 2 micron distance away from everything else, I can get a clean analysis. But my interaction volume is 1 micron. So if I'm trying to get something that's like a quarter of a micron in size, essentially I'm going to be sampling everything that's within a micron of that. So I can't get things that are under a micron in size without getting some contamination from what's around it. But fortunately, these are very large grains, so we shouldn't have that problem. So let me just start by, actually, let me put it on this setting too. So let me start by going here, and I'm going to collect the point right there. You're now going to see it collecting spectra.
Jeez.
And then I'm going to collect this spectra right in here. Okay, so this is spectrum 1. You're going to see it's got oxygen, magnesium, silicon, and some iron. You'll notice that there's a relative higher amount of magnesium than silicon. This is one of the key things I use to tell me this is an olivine. Whenever I see this pattern, I know that this is an olivine. So we'll wait till it's finished collecting, and then it'll go on to spectrum 2. And then we'll see if it's the same pattern, whether it's different, or we'll see what's going on here. Okay, so we can see, aha, you see right here, this carbon popped up?
Ah.
This is the carbon coat that's on top. So it's contaminating our analysis.
Wow.
So we know that this is not a good analysis point, and we know to throw it out. Normally, whenever you're
amazing.
doing analysis and you see things like this or things like this, these are areas you do not want to hit. They're just surface contamination.
Gotcha.
Yeah.
Wow.
So yeah, firsthand, this is how you know to separate a clean versus non-clean analysis, just from the
I
top.
picked a shitty spot, but that was a great learning thing. Thank you so much, man.
Yeah, no problem.
Yeah,
All
I'll
right.
just take an olivine next to it for right now then.
Sure. Well, I mean, we definitely need to get more grains, right? We're doing classification. So for classification of this sample, you got an olivine grain, right? So we can get a few more, and we can maybe try to sample maybe some of these other colors right here. So
Yeah, I think this is going to be my little honey pot of area. So that way when I have one picture of the thin section blown up 6x4 on my wall, I know all my spots are there.
sure.
Yeah.
So what do you
Topher,
want to
don't
get?
feel bad. You were the only person who picked that spot.
Oh.
So it looks like we've got another olivine grain here and another one here. So which one do you want me to get? I can get one of
Yeah.
each if that works. If you'd like.
Are we literally talking about the green olivine?
Yes.
only?
So yes. So these bright green areas right here.
Okay. I like the round one just under mid line on the
Okay.
left hand side.
Sure. All right. So maybe somewhere here.
That is it.
Okay. So we'll get that. You can see we got a pretty clean
Yep.
analysis here. All right. So that's good. Let me just check something really quick. Okay, cool. All right. And then now let's we can get maybe one more olivine here. So we want to get, when we're doing classification, you want to just try to get some points. So I'll just get another
Mhm.
olivine there just so we have 3 clean analysis. And then now we want to get low calcium pyroxenes. They're essential to the classification to know what ordinary chondrite group we're looking at. So that's going to be these dull greens right here.
Okay.
So any particular ones that you like, we can get 2 to 3 of them.
Yeah, just under the E. Near
Okay,
there's a big grain a little bit down further. There's 2
This
white
one?
dots. No, just over to your right a tiny bit. There's 2 white dots on it.
Okay, so this one right here?
No, go to the E electron and go down to the
Yep.
big square.
Big square.
Just go straight down to the white square, the white metal. I think it's another inch down. And yeah,
Okay.
right in that olivine. That's the one.
Right in
Yep,
here?
exactly.
Okay, gotcha. Okay, so all right, so let's get a point. And then you'll see a different spectra. So now you see oxygen,
Wow.
magnesium, silicon. Silicon's higher than magnesium. This is typical of pyroxenes. We tend to see this sort of pattern when we're in our energy spectra right here. So this is pretty typical of orthopyroxenes or low calcium pyroxenes. You can see there's very low calcium. So that's another thing that we know. And so what I'll do is if I hit this red spot next to it, you'll see right away you'll see a high calcium pyroxene once this one finishes. So what I'll do actually is I'll get a spot of every different mineral in here just so you can see what the patterns look like, just at least one of each ones. And then we can go back to getting more. So here we go. So now you see magnesium, calcium shoots up,
Wow.
and iron drops. This looks like it's a magnesium calcium rich clinopyroxene or augite. Some people might call this a diopside in terms of its composition, but I'd probably say it's more of like a magnesium rich augite, but it's a high calcium pyroxene. So we have 2 types of pyroxenes in our sample.
Wow.
And then if I go to this purple area right here, we can see whether this is what pops up. So this can, all right, so we can see silicon, we see aluminum, sodium pop up. This is a sodium-rich feldspar. You tend to find those in metamorphosed ordinary chondrites. It's got a little bit of potassium and a little bit of calcium.
No iron at all. Wow.
So if this was a glass, you would actually see a little bit of magnesium and iron pop up. That's the way you can distinguish feldspar from devitrified glass in your ordinary chondrites, your type 4s from your type 5s. It's a pretty cool trick you can use. And then what I'm analyzing next should be a chromite. So we would expect chromium to shoot up. Yep, there it is. Chromium, iron, manganese will shoot up as well. You see aluminum and magnesium shoot up also a little bit. This is indicative of a chromium spinel. So it's got an intermediate composition. Titanium also goes up, and vanadium, which is a trace element you tend to find in some of these spinel phases, also pops up. We can't really detect it very well, but you can just see just from the spectra. Let me get a troilite. So I know Pat likes troilite, so let me grab one for him. Let's see.
This is my no.
There we go. We have a iron. There's the sulfur peak. It's a troilite.
Wow.
The silicon pops up likely because I made my rectangle a little too big, so it's maybe picking up some contamination from the outside, but that's a troilite. Maybe it's been a little weathered, it's been a little altered. You know, these chondrites are sitting on Earth's surface for a while, so you get oxidation, you get alteration. Let me see if I can find a metal. Here we go. Let's try this. All right, let's get that. And then let's see what comes up. So iron, there we go. And there's nickel.
Wow.
So this is one way we can tell we have a meteorite. A lot of
Yeah.
people ask, like, how do I know if I have a meteorite? Well, if you have a metal phase that has considerable amounts of nickel and cobalt in it, and the composition matches with other phases, this is a pretty good way you likely have a meteorite. So you can see if we look at a phase like, you know, magnetite or hematite in terrestrial rocks, you don't see this nickel peak, but we see it right there. So, and this is just firsthand. We just noticed it, you know, and everything else fits with an ordinary chondrite. So all of this can be used to confirm that the composition, the texture, and the mineral phases we have are consistent with a metamorphosed ordinary chondrite. So we knew all of that just from what we just did. Yeah. So it's pretty cool.
Yes.
So I'm gonna get a few more compositions of a few more points for this low calcium pyroxene, because for classification work of ordinary chondrites, we only really care about olivine and low calcium pyroxene, getting data points for statistics. So I'm just gonna get this one, and I'm gonna get maybe, let me just get one more. Do you have a preference, Topher? I can get one more.
I would I feel like I've picked out 85 million locations, and we have a whole crew here.
Okay, Sue, do you have a preference? We can go somewhere near the top or somewhere near the bottom. I don't know if you have a preference, Sue.
I feel the same way as Topher.
I would
let's
say,
let Pat pick it since he's helping with the cameras. Pat, do you have a preference?
You gotta unmute yourself. I still
Sorry,
can't.
I picked the wrong crew member.
Yeah, sorry.
Sorry, Pat.
Yeah. Let's go down and to the right.
Down and to the right. Okay. So let's see. So for the pyroxene, we only have maybe here or here. So maybe anywhere in here that you like.
So it's the light purple, not the deep purple.
Yeah, so it's this sort of dull green. Yeah. It's like it's like green brown.
Yeah. Okay. Yeah, that's the sweet spot right there where you're at then.
Right here? Okay.
Yep.
All right. So the reason why I'm checking this is you can see all these pixels here. Whenever you do a chemical map, it runs the colors over the pixels, but sometimes you can't tell if there's cracks. Whereas here, you wouldn't see this little crack right here, and it'd be a little difficult to spot here. That's why I use this image when I navigate. So it ensures I get good data, but I'm also on the correct mineral phase. So that's why I use both images together. All right, so we'll run that spectrum. And then what we'll do after is we're going to go back and look at each of these 12 spectra that we took. And we're going to find out what kind of ordinary chondrite this is. So we'll get the phaolite and the ferrosilite values that are essentially very important for doing classification of ordinary chondrites. Okay. So now that we got the last point, what I'm going now is into the calculate composition field. Actually, very quick, let me just go into this field very quick. And let me just exclude sometimes. Okay, so it's including carbon in there. I don't really want carbon, so let me just exclude that. Sometimes I have these predefined elements that I select, but sometimes it highlights other elements in here. So I sometimes just check. See, this one has bromine. We don't need bromine in our sample. Vanadium, we don't need zinc or europium either.
Wow.
So I won't do this for everything, but I'm doing it just to show you right now that just because when you take a spectrum doesn't mean we're done yet. You have to do processing. You have to know what mineral phase you're looking at. Otherwise, you know, you're going to have all these, sometimes you get these little peaks that overlap with different elements, and you have to tell the system like what phase you're looking at. So like if I zoomed in here, like let's say I took out iron, right? Let's say that was excluded. And then I zoom in here and I'm like, what is this peak? And I zoom in here, it'll tell me like what it thinks it is. And then I hit this and it re-includes it again. So I have predefined elements that I set that I know are in different meteorite groups, but sometimes you have to tell it to exclude elements and sometimes it'll tell it to include them. So now that we've done that, now we go to chemical composition. And then now what I'm doing is I am going to go to, you can use different things. I'm going to use atomic percent here. It's a little easier. And actually, let me use oxide weight percent. Okay. And then what I'll do is, let me set it as that. Okay. All right. So what I'm doing now is I'm in oxide weight percent. So all the elements you're seeing here are shown as oxides and they have their weight percent. The key thing you have to do is know what mineral phase you're looking at because we're setting what are called the number of oxygens fixed. For olivines, just to make it simple, we keep them at 4. And so what we expect is the chemical formula of olivine for like a typical mineral like forsterite is going to be Mg2SiO4. So what that means is that if I assume there's 4 oxygens, I assume that if I add up all of my other elements, we'll call them cations, the sum of them should be about 3. And it's 3, which means I've correctly on a olivine grain. And the chemistry is pretty good, giving me a good sum. So basically for olivines, what that means is I want to see sums of 3. And when I'm looking at like a pyroxene, let me see if I can get to one. So that's another olivine. So let me just set that at 4. Set that one at 4. So we'll just check these olivines really quick. So spectrum one we saw was at 3. This one's at 2.98. This was the contaminated one. So you can see right away the cation sum is not perfect. And if you look at the total, you'll see that this total is a lot lower than this one. Ideally, you want to be near 100%. On a microprobe, it's very easy because you have high currents, so you can keep totals close to 100%. On an SEM, it's a little more difficult. So your totals are going to be a little bit off from 100, but you can see it's still close to 100. And our cation sum is 3, which is what we expect. But for our contaminated grain that had that carbon coat on top, it has a very little total, and the cation sum isn't perfect. So these are tricks that I use to also determine whether I have a clean analysis or a non-clean analysis. And then 3 is also a clean analysis. Well, let's see, actually. So the total is a little low. So the total is low, but the cation sum is clean. So we can always come back to this one, and we can check if it matches with spectrum 1. So sometimes you can get good cation sums, and the totals are maybe a little off. But I normally use the cation sums as a guide when I'm using the SEM as whether or not I have a clean mineral phase. Okay. So sorry, let me fix this again. Whenever you fix the number of oxygen, adjust this. So again, this is an olivine. And then, okay, so now we're on a pyroxene. So for pyroxenes, the chemical formula for something like a, not hypersteam, maybe a, hypersteam would be something like MgSiO3. So if we assume there's 3 oxygens, we would assume there to be a cation sum of 2. So the magnesium plus the silicon, so we can see it's 2. So this is a clean pyroxene analysis, and so on and so on. So I can do that for all the spectrum. But what I'll do now is I'm going to go in atomic percent mode, and we're going to calculate the phthalites and the ferrosilites and determine what ordinary chondrite group we're looking at. So I'll click on this. And so the way it works is when you're in, let me see if I can expand this a little bit. So I'm going to do something like that. Okay. So while in atomic percent mode, what we're going to do is we're going to calculate the molar proportion of iron over iron plus magnesium. So that would be the 7.11 over, and then it'll be the sum of 7.11 plus 21.36. And then we'll divide that by 100. Or sorry, multiply it by 100. So we can all calculate it together if you'd like. So, but I'll do one as an example. So I do 7.11, and then I divide it by, so if I were to add those together, that would be what, 28 points, what's that, 47, something like that. And then I multiply that times 100. And then I get a number of 24.98, 9798, 24.9, roughly 25. So that's a phaolite value for this olivine of 25. Okay, so we got that one. So let's do another olivine. So let's do this one right here. We'll see if it's similar, if it's different. So this one shows 7.29. And then we'll divide it by the sum of 7.29 plus 21.23. So that will be, let's see, 28 points. What is that? Is that 5.2? Something like that. And then we'll multiply that times 100. And we get a phaolite value of about 25.6. So the two olivine grains that we got were pretty similar in composition. They were only off by a small difference in their phaolite value. So we could say at least that those two grains are roughly almost the same composition. Okay, so hold on to that phaolite value of about 25. Let's now navigate to a pyroxene. So this is our low calcium pyroxene. And so what we're gonna do the same thing. We're gonna calculate a ferrocite value. The only difference is now it's gonna be the ratio of how much iron there is in the pyroxene over iron plus calcium plus magnesium. So now we're doing 4.16 divided by the sum of 4.16, 0.25, and 15.31. So
could you give the equation one more time? I'm sorry.
sure. So we're getting the ferrocite value of this pyroxene. It's going to be the iron, so 4.16, divided by the sum of the iron plus calcium plus magnesium. And then whatever number we get, we then multiply that times 100 to get a percentage. So if anyone wants to calculate this, I'll let you calculate it, and then we'll see what ferrocite value we get.
Pat, are you figuring this out? You better be. You want co-classifier on your introduction ever? You better figure this one out.
This makes me think about like the XRF test images we get, and it just reminds me of like no matter how sophisticated like your diagnostic equipment is, you actually have to know how to use it, know which tests to run, know how to like calibrate everything. And anyways, my point is anyone could probably rent an SEM, but watching Daniel in action kind of demonstrates how much knowledge is actually needed to utilize everything correctly.
Yeah, I was taught that the easiest thing to do is navigate on the instrument and collect data. The hardest thing is to navigate on the instrument and collect good data and know how to process the data. Because most of the work that's actually done in the classification really is processing this data after you collect it. Because you have to make sure you have clean mineral analysis, because it's important to get this data as we're seeing here. So my advisors
did a great job.
my advisors have really helped me with improving my data processing skills. So that they're very good at taking a data set and extracting the clean mineral analyses from there. So I've learned a bit from them on that. So yeah.
Nice.
So did anyone get a ferrocite value, or should I say what I got?
Did anyone get that value?
All right, so I'll say what I had.
Yep.
So I got 21.2. So if you got 21.2, that's correct. So let's remember we have a ferrocite value of 21.2. So let's get another pyroxene just to make sure it's roughly the same. So let me see where I found those other pyroxenes. So this is kind of where I go back and forth. So I knew that spectrum 11 and spectrum 12 should be clean low calcium pyroxene analyses. So now I go back into these, and now I can get the ferrocite numbers from these. So let's do another one right here. So if anyone wants to calculate the ferrocite value with me, we can do that again. Okay, did anyone get the value? Or is anyone calculating it?
I have everyone on mute. I hope that if you want, you can unmute yourself. I'm working on other stuff in the background. I didn't work it up. Is it 21.2, I hope?
That's correct. Yep,
Nice.
21.2. All right. So you can see it's exactly the same between both points. So like the olivine, where the phalite value was 25 and then 25 point, I think 4 or 5, this
Mhm.
ferrocite value is consistently at this 21, 21.2. And I can just quickly hit the other pyroxene, and just sometimes what I do is, instead of doing the calculation, if I look at this one and I know what the value is, and then I go to this one, I could see the iron is kind of about the same. The calcium is essentially the same, and the magnesium is just the same. So I know right away this composition is going to be basically almost the same as the other one. So once I kind of know like what one phalite or ferrocite value is, I can then just scroll through the other olivines and pyroxenes and see if I get similar numbers. So that tells me right away whether I'm looking at equilibration that took place, which you get in type 5, type 6 chondrites, or whether or not I'm looking at something unequilibrated. So that's one of the tricks I use.
That's key, yeah. Okay.
Yeah. Okay, so now that we know the phalite and ferrocite value, I'm going to just quickly, let me do something. Let's see. So now let me get a diagram, and let me see if I can find a pretty good diagram to show that will have this on here. So just give me 1 second.
Mhm.
Okay, so, all right, let's try. Okay, let's try this one right here. Let's see. Okay, so I'm going to share my screen very quick, and I'm going to switch to this chart right here. Okay, so what you're seeing, there's many charts that have this. I just picked the first one I found on Google, but basically for ordinary chondrites, for the H chondrites, which are in red, the L chondrites are in blue, and the LL chondrites are in green. For the equilibrated groups, it's been known that there are very specific trends that you tend to find in the olivine chemistry, which is what this y-axis is, the phalite value, and the pyroxene chemistry, which is the ferrocite value. So what you do is you literally just plot them on this chart, and we find out what group we fit in. So the ferrocite was like, what, 21? So we're somewhat here. And the phalite was 25. So we're essentially at the upper end of L chondrites. So this is one of the tricks we use that's very important to tell us if we have an H, an L, or an LL. There's other tricks you can use. You can measure magnetic susceptibility, which those values essentially are also known for these different groups, and they're somewhat distinct. You can look at things like Condrule size, which is good when you're looking at type 3s that are unequilibrated, in which case you can't use this system. You can look at things like the relative amounts of metal or the relative amounts of different mineral phases. But the easiest way to know like what meteorite group you have with the chondrites is to use this chart right here. So just by using this,
what does the green represent again?
the green
Ls?
is LLs.
Okay.
LLs. The blue is Ls.
So we're right on the threshold of an LL or an L, but safely in the blue L.
Yeah, I'd say we're probably in the L. There are, of course, stuff that overlaps, but based off the fact that I saw a lot of metal in this sample, and it looks more like an L to me, just based off of saying that. And there are, of course, other plots. So let me get, let me try this one right here. Let's see. So yeah, so you can see now this is another one. 25 is here, 21 is like here. So we're still in L. So some of these, they're not all like the threshold from one to another is a little different depending on what paper you cite. But when you see a phalite value of 25 and a ferrocite 21, that's a sure L in most cases. Yeah.
Sweet. Thank you.
So that's all right.
So we have one part of the classification.
Yep. So we've got one site. We have 3 olivines and 3 pyroxenes. So we've got quite a bit more to go. So obviously on the other sites, we might not spend as much time, in depth doing all this, but we will collect a lot of points. And so let's get to that. So
just to clarify, Daniel, all these points of data you collected right now are all that data is compiled into one point. Is that what you're saying?
So yeah, so all of these spectra points, what you're seeing right here, they're all compiled to here. So we collected data right here. That's the spectrum. It's saved. So we can always go back to it and see what data we collected from that spot. And it's the same for all 12 of these. So this data is saved. We've already saved it, and we can come back later to do data processing.
Okay.
Okay, so we're all set. So where shall we navigate next?
Is Art ready?
I believe so.
Right on.
Yeah, I'm looking at the blue dot.
Okay, the dark blue or the light blue?
The dark blue.
Okay, the dark blue. Okay.
Yep.
All right, so let me save this point really quick. So in case I get lost, we'll save it. So what I'm doing now is I'm going to navigate to that area, or at least as close as I can. So let's see. So if I go to the right, I would expect us to get off of the Condrule or whatever we're looking at there. I can see there's a, let's see, I can see there's a metal grain there. Let's see if I can, okay. All right, here. So now I'm getting into the, okay, so now you see all this sort of color right here. So let's see, I'm just going to zoom in really quick. So it looks like I'm in a shock darken zone. So you might hear the term shock darkening and shock melting. Shock darkening means that during shock metamorphism, which is essentially when this object was on its parent asteroid and it was hit by a hypervelocity collision, the high increase in pressure led to a huge temperature spike, and you essentially melted a bunch of metal and sulfide that then formed these blebs and navigated through these networks. So it essentially darkens whatever you're looking at. So that's why it appears dark. So this is shock darkened, or actually, no, it's shock melted. Sorry.
Yeah,
So
no.
shock melted means that you've also melted the silicates. So if I were to take an image, you could see this. This is typical texture of something that looks like it crystallized from a melt. So we're now entering that sort of shock vein. And so now what I'll do is I'm going to follow it up because it's moving, it's trending northeast. So if I follow this up, it should then go this way, and then it should turn back northwest. And then that should be, I think, the spot that you were interested in. So let's see if we can find that. All right, so we have this pretty large metal grain. Let's see, I think that's up here. Actually, I think that might be the spot. Let's see. Let's see, it's branching out this way, and there should be another one to the right of it. Maybe this might be a little bit too high. Let's see. But I would expect there should be a Condrule nearby, which I do see it, and there's the vein right here. All right, so it looks like we're on the spot.
Okay. I was interested in that area of shock and the visible grains within the shock vein, the so-called high pressure mineral grains. And
Okay.
I was wondering how they differ from the other mineral grains in the specimen piece, because I believe they're also silicate minerals and maybe a few sulfides.
So that's a great question. So what can happen is you can definitely form during shock metamorphism, when you form these shock melt veins, if you have things like pore space collapse, frictional sliding, you can generate essentially from melt these new mineral phases that, because of whatever you're melting, controls what you're forming. So they're likely silicates, but they might not be the same mineral phase. You could get things like garnets under a very high pressure. You could get olivine with a different structure, like a ringwoodite or a wadsleyite type mineral phase, or you could get other minerals, or you can get the same mineral composition. So we can definitely navigate in there. So I can go right into the center of this shock melted area right here. And then I'm going to go at a very high magnification.
Wow.
So I'm going to go as far in as I can. And we'll take some points. Now, the thing is, because I'm going pretty far in, we have to worry about the spot size of when I'm doing the chemical analysis. So it might not be perfect,
Mhm.
and we might get overlap between different mineral phases, but at least, you'll
Mhm.
be able to see whatever's in here. All right, let's see. And it might not be perfect. The further in you zoom, the more or the less space you have to navigate the focus. So let's try this.
Wow.
Okay, so let me see if I can go further. 3.5. All right, so anything in here is 2 microns. So these grains are like extremely small.
Yes.
All right, so let me scan this image, and then I'm going to share my screen again. Now you can see that it's not going to look as sharp as the previous one because we're at a much higher magnification. So our
Mhm.
depth of field or depth of focus is very slim, and we're not obviously going to see a lot of these very small features very well. But you can see in this shock melt vein, we look like we have silicate minerals that are very small. You can see they're
Mhm.
almost clustered together, and it looks like they may have crystallized from this shock melt.
Mhm.
And
Mhm.
so what we can do is I can run a chemical map, and we can see if they're all, what mineral we might have. And then I could even maybe get a few spots if I can find a large enough grain. And we can see what the composition is and if it matches what we got from the previous site.
So if I understand it correctly, the event that creates the shock melt vein happens very, very quickly. So it stands to reason these high pressure mineral grains are going to be very, very small because they're not going to have enough time to grow or slowly cool. Now, the pressure that's generated, the dark shock vein, does that have any effect on the formation of the high pressure mineral?
That's a very great question. And if Vince was here, I'm sure he'd be extremely excited to answer that. Is it all right? But I will take a stab at answering that question. So the formation of high pressure minerals by default requires that you have to be at obviously elevated pressures compared to things like atmospheric pressure. And so what a lot of work that's been done so during, of course, the hypervelocity impact process, you have a shock wave that's transmitted through a heterogeneous material that has all kinds of different phases with various densities. And so as this shock wave is being transmitted through, things like density differences, things like the amount of pore space you have, porosity, what material you're moving through, how close you are to the source of where these shock waves are coming from. All of this plays a large role in the peak shock pressures or equilibrium shock pressures you would experience. Now, there are certain areas where you can get things like, for example, if you have a pore that's collapsed or an area that undergoes frictional slide, you can get even higher increases in pressure. We call these localized PT excursions. And in these specific regions, you can generate things like melting. And because this occurs very quickly on orders of less than a second, depending on how big, the impactor was, some cases milliseconds, you can sustain high pressures for enough of a time scale where you can melt the object and later crystallize high pressure minerals from it before the pressure drops. Because the key thing is if you form a high pressure mineral, but then the pressure drops very quickly while the mineral is still hot, it'll just revert back to its low pressure polymorph. But if the pressure stays on high enough, but the temperature cools very quickly and the rock quenches, you will preserve these high pressure minerals depending on what sort of pressure temperature regime you're in. So what I will say about this is that basically people look in these shock melt veins, they try to identify what high pressure minerals they find, and then based off of that, they can equate how high the pressures and temperatures were that must have created this vein during shock. Because there's been a lot of work studying like what pressure range a mineral like garnet or ringwoodite would be stable under. So that's kind of how a lot of these studies work, is that you look in these veins, you find minerals, and then you try to fit them with models to like come up with how they may have formed. it's a really cool thing. Vince is doing a lot of work for that for his thesis right now.
Yeah, it amazes me because shock veins can record more than one event of shock. Is that correct?
That's absolutely correct. Yes, they can record if you have a second event. They can record things like temperature timescales, where like in a shock melt vein, as you get as you get closer to the edges of where the vein meets the host, you can see different mineral assemblages. You could see the same assemblage, and this all tells you about the temperature, pressure, time pathway that this area underwent during shock or progressive shock events. Yeah.
That's amazing. Wow.
Yeah. So now that we've collected this map, it looks like we have a mineral phase in here that looks, this sort of red phase, it looks to kind of be relatively consistent as taking up most of the space. So we can get a few points of there. I don't know if you have a preference on where you want us to get a point from.
You know, I'm just amazed to pick any section that you see that looks interesting.
Sure. Okay. So I'm going to have to look for areas that have large grains to avoid things like, okay, so this grain is about 2.5 microns. So I'm going to try to get right in the center. Let's see what we get. Okay, so this is interesting. So it looks like we're getting something that's like a pyroxene, but you can see there's a bump in aluminum and a bump in sulfur. So this could be one of two things. The sulfur could indicate that we are getting contamination from some sulfide minerals. That's sort of this bright stuff that's around it, which makes sense. You can see it's sort of yellow. This is what a sulfide would look like. The aluminum peak could indicate that we're melting, for example, a mixture of feldspar and pyroxene, and we may have formed something like maybe a garnet in here, which garnet can accommodate aluminum into its mineral structure. And garnets tend to have these sort of euhedral-like shapes. So this could be potentially, I'd have to check the chemistry, something like a majorite type garnet, potentially. This could also just be some kind of pyroxene, but because I'm seeing some aluminum in here, this would be worth checking out later. But if we compare this with the previous low calcium pyroxene that we had, you can see there's no aluminum here. So we do see a slightly distinct change in mineral chemistry in the vein versus outside of the vein. Yes.
Interesting. Interesting. Wow.
And there may even be a hint of zonation. So I'm going to get this area right here and let's see how it compares.
Okay.
So let's see. So you can see this area has a little bit more magnesium. You can see it's darker and you can see there's more green here. So that means there is maybe some zoning that's going on in these grains, meaning that the time it took for them to crystallize very quickly must have exceeded the time scale of what we call interdiffusion of magnesium, meaning that there's zoning that we can see. So this means that these cool very quickly. What it also tells us, which is also interesting, is it tells us the relative time scale on when this shock event took place versus when the entire rock was metamorphosed. So as we know, ordinary chondrites that are type 4, type 5, type 6, these have been metamorphosed or heated on their parent body. And so essentially they're like metamorphic rocks on Earth. You just heat a rock and essentially it changes the texture, your chondrules get blurred, your coarse in your matrix size, and your minerals become equilibrated. But now in this shock vein, I'm seeing evidence for disequilibrium. So what that tells me is that this shock event took place after this host meteorite underwent metamorphism. So I can now put a time scale to when things took place.
Wow.
So it's really cool just by, going in this vein and getting chemistry.
It reminds me of being a forensic detective. You have a crime that has taken place, and now your job is to determine with the clues that are presented to you to put the puzzle together and predict a time period and what exactly took place. That is amazing, Daniel. That must be so gratifying to you. I can't imagine, something like this, as complex as this, that you just analytically break it down, clear, precise, and you know, it is what it is. The science is there. Science does not lie. And, you know, it's got to be great satisfaction to you when you do identify and classify something, because there's no question it is what the instruments of detection have told you are in the piece, and it can be nothing else but. So, yeah, excellent.
Thank you. Thank you. Yeah, this is essentially, we're working with the limits of what we can. So whatever we can detect, we can detect. Whatever we can, collect data from, we can. Fortunately, for pretty much every meteorite group, we should be able to get enough data from this. But if you wanted to investigate, inclusions in these small things, we can't do that with this system. You'd have to go to something like a transmission electron microscope, where you can see stuff at the nanometer scale much better. But yeah, at least fortunately, we can see inside this really cool shock vein. And this kind of fits with the shock stage I had determined for this meteorite. I had it at about S5 based off of seeing things like mascalinite in the host. And the fact that we're seeing things like this, potentially majoritic garnet would be consistent with also shock pressures of that high.
Wow.
So
Nice.
it's pretty cool.
Nice.
Yeah.
Absolutely.
Yeah.
Thank you so much.
Yeah, no problem. So where should we navigate next?
I think Bruiser is the next driver.
Okay.
So I was looking in between where the blue and the purple dot are at about 7.5 down. I think the scale is kind of big, but it almost looks roundish. So wondering about if that's like a Condrule that partly survived. Actually,
Sure.
there's a couple little ones.
Sure, we can definitely look at that. All right, so what we'll do is I'm just going to move to the right, and then if we see any really cool large chondrules in there, or like chondrule outlines, we can definitely get some cool spots of those. So let me do that. All right, so if I just move to the right, that should take us there. So okay.
Yeah, it's really hard to tell like the different scales of things.
Yeah, so let's see. So let me see if I can do some chondrule identification 101 here. All right, let me try this. So I'm just going to be at a high scan speed. Okay. So it might be a little hard to see this, but there are chondrules in the object. And so if I were to point it out, you'd see this rounded object right here. This is a chondrule. This rounded object right here looks like potentially a chondrule. This looks like it may have an outline of a chondrule right here. And this thing may have been a chondrule at some point, and maybe this thing. So what's happening here is as you heat this sample and it metamorphoses, the matrix, which usually is very fine grained, it coarsens in grain size because it's undergoing slow, it's being heated. So the grain size is going to grow. So what ends up happening is then all of a sudden this grain size of the matrix is the same grain size as that in the chondrules. And as that also is going on, your chondrule glass or mesostasis, which is something that's very easy to tell that you have a chondrule, that recrystallizes and turns into things like secondary feldspar, which is what this dark gray is here, and high calcium pyroxenes. So what I'm going to do is I'm going to try to highlight potential chondrule outlines here. Let me wait for that to load. Now it's very tricky sometimes trying to perfectly define chondrule boundaries when you have very equilibrated samples. But sometimes you can use tricks like when you see things like rounding of this metal and troilite that kind of looks like it's sort of going around like a chondrule rim. That's one thing I kind of use. Let's see if I go maybe something like that. So maybe something like that, may have been a chondrule, or something like maybe that, or maybe even let's say something like this. Chondrules are one of the things that it's actually a lot easier to see, believe it or not, in a thin section using transmitted light than in backscatter electron imaging. It's actually kind of funny that you can see chondrules better with an optical microscope than with these. But yeah, these are some of the I believe would be like possible chondrule boundaries. Maybe this would be another outline right there, and then maybe we're getting like a small edge of like that one right there. So this might be a porphyritic chondrule, or maybe a bard. So this maybe would be a bard, and maybe these are porphyritic chondrules that all of a sudden now you're starting during metamorphism. These grains are like attaching together as they're growing, and then these might be like granular or cryptocrystalline ones. So, but you can see these do look like chondrule outlines. So there are some in our sample. Yeah. So do you want me to get a spot near any of these chondrules and get some points and run a chemical map?
Yeah, I think the larger one that you think has the battle, right? Yeah, right where you are right now.
Sure.
That whole area.
Sure. So I'll go somewhere in between maybe these two, and then we'll get a chemical map. So let me navigate back to the other. So let me stop sharing this and then navigate back to the original. Right here. Okay. All right. So I'm going to go right in between these two big chondrules. So I'm going to go to higher magnification. I'm going to get this in focus. Some of there is good. So normally whenever I zoom in and zoom out, I don't have, sometimes I get these little brightness issues on the SEM. Not all the time, but sometimes. Today the system isn't acting perfectly, but at least it's working all right. So I'm in between now both of these. So I'm going to go to maybe, let's go 400x, somewhere there. Just lower that a little bit, like that. And then let me now share my screen.
Daniel, can I just interject here for a second? We have a lot of new people joining us right now live, which is awesome. And I just wanted to make sure that we show appreciation for that. But I also wanted to ask a question. Maybe you could just 20-second verify that the information is correct.
Sure.
When we see how detailed and how granular and how much zooming you can go and test, there is a desire instantly to go and test everything on there, every little color, and just understand everything. But that's just our science. That's just our inquisitive mind. Science and the classification process only cares about certain bits of data from this. And if you could just, if you have any comment on that, I'd appreciate it.
Yeah, no, that's a really great point, Topher. And it's important to understand that on one side, it would be great to sort of just look at everything, find out the composition of every little point, and look at every single chondrule in the sample, every single area. But with classification, there's a strong balance you have to find. You have to know how much information do I need to get, and how much information, do I not need to get? Meaning that, do I really need to go throughout the entire sample and look at every single chondrule, or can I navigate through the sample one time, and see that it looks all like it has the same texture, and then maybe go to like 3 or 4 representative sites and just collect from there? And we tend to do the latter because, to form this rock, right, at such of a small scale, if you see that the texture is consistent and the mineral chemistry looks the same, you don't have to go to every single area and get points.
Mm-hmm.
I've had some people email me about, the fact that I may have looked at like 3 areas the size of a hairpin on their sample. Why didn't I look at all these other 50 locations to determine that maybe one of those was meteoritic and the rest of them were terrestrial? And the reason being is that when rocks form, understanding how different rock types form on this scale, whether you're looking at one area or another area, as long as the texture is consistent, and the mineral chemistry looks to be about the same, you don't have to go to every single point. Even when you're looking at breccias, like lunar samples that have different clasts, you don't have to sample every single clast. You could look at like some that are representative of one group of clasts and some that are representative of the other group. And that's where the time aspect comes in, because so for example, we're on, what is it, this says site 6, but really we're on site 3. So let me just call this, so this is site 2. And then we're really on site 3. So you can see so far in the amount of time we've spent, we've seen a lot of really cool things, but we've only gotten a small number of points. So this is sort of the trade-off that you do with classification. How can you efficiently manage your time, if you have a few hours, to get the most representative data you can that's enough for the classification?
Yeah.
We're not
Thank you very
doing
much.
like research quality work to the extent that we're really going in and getting everything. You could
Yeah.
down the line. We're doing the
Yeah.
first work.
It's a balancing act of what is needed versus how much time do I have dedicated to me on someone else's device.
Yeah.
Wow.
Okay, so this,
What's that orange over there on the right-hand side?
great question. All right, so orange, we can make this by a combination of red and yellow. So we can find out right away what this is. So let's go in there. Let's get a point. And let's see what we got.
I'm sorry if this was Pat's turn, but or if we're still on Bruce's turn, I forgot.
All right, so we got calcium, phosphorus, and chlorine. This is a chlorapatite. So this is the mineral phase. So these are actually very cool minerals because you can actually date these minerals using different isotopic systems, and you can get ages from these minerals. So someone could look at this phosphate, get an age, and that could tell you the age as to when maybe this meteorite was heated on its parent asteroid. So it could be, very old. It could be relatively young, right? These are research quality minerals that a lot of people like to find for doing things like isotopic dating. So whenever you find one of these, it's useful for research work. We don't use them in the classification, but on the form, I can say that this is an accessory phase that we find.
Cool.
Yeah. Okay, so I can get a few olivines and a few low calcium pyroxenes. So does anyone have any preference for where they want me to go? So ideally, what you want to think about is think from the mind of a classifier. Think I can only get 3 or 4 olivines and 3 or 4 low calcium pyroxenes. So from these bright green areas, if I can only get 4 points, what are the most 4 representative points that can tell me the most about what I'm looking at?
Oh, so are you aiming more for like center mass type things?
So
Because the way you kind of led that there makes me not want to go near the edges of anything. Makes me want to go dead center.
Right. So it depends. So you can see this green is all the same color. If it was different or the color was varying, that would tell us this olivine is zoned. But we know that it's equilibrated. So whether I hit here or here, I'm gonna probably have a very similar, if not identical, phthalate value. So now it's just a matter of where can I get the cleanest spot without hitting cracks or without hitting small inclusions. But where can I get a spot that's representative of where I'm hitting? So if you get this small little olivine grain here, that might be cool. But if you sample here, maybe you're getting more of a representative sampling of this larger mass.
Very interesting. I did not pay attention to that at all when I was picking my spots or looking at this originally.
Yeah, it's a tricky thing. This is something that, it just comes with when learning. Like, so whenever I see this, I'll tell you where my mind goes. I immediately think
right there at 1 o'clock.
there, and there. Yeah. That's where my mind immediately thinks. And then for the pyroxenes, I go here, 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 and here. Because I try to, get representative from like each part. If I just get grains here and I'm missing here, I might be missing something. So I can I'll show you what I do. So I just go here and then I find a clean area. a rectangle. And normally I sometimes do this a little fast. So if I'm going a little fast, let me know. But I kind of just
This is cool to be inside your brain when you're doing this.
so I'm going at the classifier speed, just, if that makes sense. And it can get a little weird seeing two images, but you know, it's just very helpful for, you know, trying to look for that. So like, so here's an ideal location. You can see there's not too many cracks, but see here, I see these little small cracks. So then I navigate around and then I find this area, but then I see this little contamination. So you're playing a game. It's really cool. You're like navigating around and trying to find like the best spots to get, you know, data. It's kind of fun. This is like one of my favorite parts of doing it.
Nice.
Yeah. And then let's say, all right, so
and it's really just in case you run into anything just wacky, weird, like that orange thing. I mean, even a novice like me looks at that and goes, wow, orange, what the hell's that? You know, that's got to be just an everyday occurrence for you as you're going through your classification or your studies, and you look at something, you're like, whoa, what is that doing in there?
Yeah, all the time. Every time I look at a sample, you know, anything that out of the ordinary is something that you're drawn to immediately. So, you know, that's why these chemical maps are so helpful, because, you know, otherwise, if you're just looking at this map, right, you're like, I have to sample this and this and this, you know, but here I know just from the color chart that this is a troilite, this is a chromite, this is a metal, this is a phosphate, feldspar, pyroxene, olivine, high calcium pyroxene. Just from that.
Jeez. Did we get Bruce's spot picked out? I just want to make sure that we.
This is my spot.
Okay.
And Chris Sanders has a question that he put into the chat. Daniel, he wanted to know, how long would it take you to do a complete analysis for the stone if you didn't like have to stop and talk to us?
Great question, Chris. It depends really. For, you know, large thin sections like this of ordinary chondrites, or most ordinary chondrites in general, probably closer to an hour, generally speaking, maybe a little more. When it comes to things like lunars and other HED, especially HEDs, those can take a lot longer. So the more brecciated a sample is, the longer it's going to take. Like if I see, you know, large clasts. For me, the samples that take the longest are those brecciated howardites, because you have to look at all of the eucrite and diogenite clasts, and to me those are and Chris, you sent me a lot of those, and those are really cool, but they take a lot of time to work on. But they are very satisfying when you find unusual clasts in some of those howardites. So that's another cool thing. And with lunars, you know, I generally spend a little more time on those just to see if I can find some weird clasts, because those are relevant to my research. So I try to you know, spend more on there. But yeah, ordinary chondrites that are very equilibrated, unbrecciated eucrites that are basaltic. What else? In some cases, things like, let's see, what else? Yeah, basically any sample that's like equilibrated is a lot easier to do than unequilibrated brecciated samples. Yeah.
That makes sense. Thanks, Daniel.
All right, so I'm just checking the ferrosolite and phalite values. So just very briefly, this ferrosolite value right here, we just roughly look at it, it looks to be roughly consistent with the other one we had. Maybe it's a little less than 20. I don't know if someone wants to calculate it, but that is roughly consistent again with L. And if I go back to this olivine here, you'll see it's like 7 out of maybe 28. So that's roughly 25 on the phalite. So this is consistent with the first area we were in. So this is pretty good. So it looks like it is equilibrated in different parts of this meteorite. And again, it's consistent with an L chondrite. Now, the only other thing I haven't talked about is assigning the petrologic type. So the key thing to note is that a petrologic type of an equilibrated ordinary chondrite can be either 4, 5, or 6. And so for a type 4, the criteria is you have devitrified glass and maybe some heterogeneity in the pyroxene composition, and really not much feldspar, or if you do, it's very small. A type 5 chondrite has equilibrated olivine, equilibrated pyroxene, and feldspar, so that's the purple, that's between, on average, 2 and 50 microns in size. And a type 6 has feldspar that is on average greater than 50 microns. Just look at the purple and we can look at the scale bar and we can kind of just see like what is the average size. And if this is 50 microns and I just sort of, navigate around, you could see that, this looks slightly larger than 50 microns.
Yeah.
Some, of course, are going to look a little smaller. Like some are very small, some are larger. So what you do is you can go into a software like ImageJ and you can just measure the lengths of each of these grains and then just get a running average. I kind of like to just look at the sample in its totality and look at different areas and try to see like, is this consistent? Because sometimes you might see like a coarse size like this, and then you go in a shock melt vein and it's like small or large, So that's why I take a lot of images, because I can also assess if I'm looking at a type 4, type 5, or type 6. So very important to look at this feldspar grain size. Yeah. All right, so now we're on site 4. So where should we navigate next?
Okay, so I think that's me. The yellow dot.
Okay.
And the thin shock vein between two thicker ones. And the thinking was, from a conversation with Vince, an area that had high shock but cooled quickly.
Okay. All right, let me get this. Okay. All right, so I'm gonna unshare my screen and we're gonna try to get there. Okay.
So it's generally in the upper left quadrant.
Gotcha.
Of the thin section.
Okay. So Pat, speaking about your type 3s, so I have gotten those thin sections back. So I'll contact you about those. All right, so let me go to, let's go there. So I'm now navigating to this sort of crack that's in the middle of the sample at about 5.5 millimeters on the left side. And I'm going to be moving in and trying to follow to get to that thin vein. So let me see if I can get there. So lower this. Okay, so you can see there's a big Condrule right here. Porphyritic olivine, maybe porphyritic olivine pyroxene. Now we're entering this, there's a little barred Condrule right there. We're entering this melt vein right here. Let's try to navigate up. We can see there's a small thin one, and I believe the next one will be this shock melt vein that is, let's see if I can find it. Let's see here. Okay, I don't think it's this one. I think this one is a little too high. Let me try.
And we don't have to get to that exact spot, just a thin shock vein near the thick ones.
Sure.
Thinking that cooling rate was quicker.
Gotcha. All right, let's see. So let me try. Let me just navigate back really quick.
So you're saying, Pat, you're thinking if a shock event happened and it happened resulted in a thinner shock vein, that there's different high pressure minerals in there than the wider one?
Yeah, so Vince was saying that on the very wide shock veins, they're so large that they're that shock level can dissipate versus the cooling rate, and minerals can flip back to their low pressure polymorphs. And so my thinking was a narrow shock vein that would have cooled very quickly that possibly could have preserved some of the high pressure polymorphs.
Interesting, thanks.
Okay, so we're at this junction. So if you kind of see this makes like a V, that's that large shock melt vein. That's where that that pink dot is. Be somewhere here. There's this noticeable Condrule to the right, and then if we navigate this way, this is your shock melt vein right here, that thin one you were talking about. So
that's it.
Would you like me to sample it here? Would you like me to get closer to the large vein? Do you have a preference? I could be near this Condrule here.
Maybe a little further away from the main vein.
Sure.
And just go ahead and pick the spots that you would pick, and please think out loud for us. Give us your rationale.
Sure. All right, let's see. So if I'm going away from the vein, so if I want to get close to the host, I probably would go here, because at least I'd be maybe sampling some of this material, which could be good for getting more olivines and pyroxenes. If I go
Okay.
further out, I'm seeing it's kind of thinning a bit. That
Mm.
might not be good. So probably here seems to be a good
Go
area.
with.
Let's go there. So I'm going to zoom in. So, all right, let's see. So now the tricky thing is when you're looking at very small objects and then you're trying to compare them with these larger like host materials, you have to find a good magnification. So I'm not going to go if I go too far in, I kind of miss seeing this stuff up here, but if I go too far out, then you can't see the texture. I'm going to try to go to maybe like 500. Let me try 600. Actually, hang on, let me zoom in first. I have to get this in focus. All right. Let's see.
Daniel, those tiny, tiny little pinprick holes that we're seeing, are those real? Are they event of making the slide, or are they little vesicles, little voids?
That's a great question, Topher. Could be either one. Generally speaking, when you're doing the polishing to make these thin sections, you could pluck out some very small grains. That happens. But if you have a porous sample on a very fine, scale, there could be vugs or vesicles, especially with stuff that crystallized from the melt, like maybe in a shock melt pocket. So could be either one. I'd have to check in with the literature on that to see what's consistent, since I don't study these, but that's a great thing that you noticed. That's a very, very good observation.
The reason that it stood out to me is because it's only in the creamy melt. It's not in the harder plated stuff above it. If that's my technical term for it.
Yeah, that's a great point. If you only see it in this area, that would be, of course, favoring the idea that this might be some kind of vesicle or vug, that, this thing crystallized very cool. It was losing a lot of, volatiles from this. And, you tend to see these in things like lavas that chill very quickly on Earth, and basalts, vesicular basalts, scorias. All right, so let me share the screen now. Let's take an image. So the other thing I'd like to point out in this sample that I noticed is when the feldspar is very coarse, when you get type 5, type 6 samples, you can see it quite well in transmitted light using like plane polarized light, cross polarized light. And you could see this feldspar is extremely smooth, like almost too smooth. There's no fractures. This is because it's transformed into a glass that's called maskelinite, which forms at relatively higher shock pressure. So starting at about 20 gigapascals of pressure to get this transformation to take place. You can see there's cracks that lead up from these silicates up to the glass. This can indicate that this glass may have seen like a density change and may have expanded, thus cracking into the surroundings. So these are some really cool things. There's a lot of research work trying to find out how you form this glass. I'm not going to go in depth on that, but it's really cool to see that we see this maskelinite glass in our sample, which we expect when we have these shock melt pockets or shock melt veins, right? High pressures to form this.
This is such a cool zoom in crop of the meteorite right now.
Yeah, wait for the element map. It gets better.
All right. So for reference, for everyone asking, this is the host meteorite right here. Here's the contact, and this is the vein.
Okay.
So we might not see everything in the vein. You can see there's very tiny objects in here. We might not see those, but we can at least see, maybe we can pick them up with a chemical map, and maybe they're similar to what we saw in the previous shock melt vein, or maybe they're different.
Okay. Now that black spot in the upper left, is that likely to be carbon again?
Yeah, I think that's contamination. Whenever you see like stuff that looks like that and has this little halo around it, it's normally contamination. Yeah.
Okay. The slightly darker gray arrowhead-shaped piece a little down and right of center is interesting.
Oh, this?
Closer to center. Yeah, if you go to center point, then drop down just a tiny bit. Yeah, that darker thing right there.
Yeah, gotcha. Yeah, there's a lot of work that's been done trying to understand that sometimes during shock, when you form these melt veins, you're breaking off material from the host. So imagine like something in like a river, like you're dropping like like objects like leaves in a river and they're floating downstream almost. So you can imagine some of these blocks of materials were broken off by the shearing event and incorporated into this melt vein and sort of dragged along or moved a little bit. That could be potentially what may be going on here.
Okay, interesting.
I don't think I've ever seen melt this close up before.
And another factor with the vesicles is that most meteorites have some grain porosity in small voids around the grains. And then when you melt that material, you don't have enough material to fill the whole space. And so you wind up with vesicles because you've got, you didn't start with 100% solid material.
Yeah, I mean, if you had a really porous object and you try to compress it, you could reduce your porosity, in which case you wouldn't completely fill in those pores. So if you were to cut the object, you might still see them. In some cases, you can actually increase your porosity, which is what happened which is why we have things like regolith on the moon, on asteroids, where you've just smashed rocks so much from impacts that you have a very porous, very, unconsolidated sediment on top.
Right.
So yeah, impacts can do a lot of really cool things. Vince and I and our group, we consider hypervelocity impacts to be, if not the most fundamental process in shaping our solar system. After, of course, things like igneous differentiation, forming a crust, a mantle, and a core. Impacts played a huge role in in the formation and evolution of our early Earth.
Mm-hmm.
All right, so Pat, I'll let you navigate.
Wow.
You've experienced some co-classification in the past, so I'll let you choose, since you have some experience. Where would you like to sample? We have the host material and we have stuff in the vein.
Okay. The high calcium red material, kind of a little lower from, or up around that grain is fine too.
Sure.
That looks interesting and consistent.
Okay. You can definitely get a good area. All right, get one there. Yep. Okay. There it is.
And then maybe an olivine that shows a nice large area to see if our facilite number is consistent.
Sure. So we can go, if you want, we can get an olivine up here. We can maybe get one here, and then we could check in the vein to maybe see if the phalite's the same for these big olivines.
That's an interesting idea.
Sure. All right. So let's check right here. So let's get a olivine point here. Let's also get one, maybe let's get another one in the vein, maybe on this side. You can see there's kind of some, it looks like it's maybe been in contact with this melt, and maybe it's been altered. So we can check that. And then let's get a few in the hosts. So you want to, if you had a preference for any of these olivines here.
Go for whichever one you think looks good.
All right, let's go for this one right here. And then let's just get one more somewhere here. Let's see. Probably there is good. Okay. And then let's get a few low calcium pyroxenes, just so we have a few of those to get frost light. So where in the host would you like to get? We have this region in the upper right. We have some in the center, a little on the left, and then maybe there's some in the vein. We'd have to check.
Maybe one in the center, and see if we could find one in the vein that's good enough.
Sure. All right, so let's get one here. Let's go into the vein. Let's see. So maybe this word. Get that. And then let me grab another one up here, just so we have a couple of points. All right, let's get that one. And then, yeah, just for consistency's sake, I'll get just one more, just so we have a good assortment. Sometimes, like I said, whenever you get points, you might have like contamination. And so it's always good to just get a little extra just in case.
Right. Okay.
Yeah.
Now, the SEM cannot distinguish between crystalline olivine and a pure olivine melt, correct?
What we're getting with the X-ray detector is only the chemical composition. So we don't get any structural information, not from EDS. We'd have to use a different detector for that. That's the electron backscatter diffraction.
Okay.
Yeah.
EBSD, right. Okay.
EBSD, yeah, exactly.
And Raman spectroscopy also tells us something about structure too, doesn't it?
Yeah, you can use Raman. That can tell you things about crystallinity. So you can take the thin section and you put it under this laser, and you can essentially, it can, depending on what sort of patterns you see, it can tell you whether you have something that's crystalline or not. You can use something like XRD, X-ray diffraction, where you crush up pieces of your bulk sample, put them on like a piece of tape, and then just pass X-rays through them, and it can tell you whether you have amorphous or crystalline material. EBSD is good for thin sections. You can do EBSD and you can get chemical data at the same time. So they work in tandem. But yeah, there's multiple techniques you can use. But you can even use things like optical microscopy, where you can, you can just look with a petrographic microscope at, minerals. And if it's a glass, so for example, this mascalinite, if it's a feldspar and at cross-polarized light, you'd see, you'd see interference colors. For mascalinite, it just goes completely extinct. So that's like one way you can tell if you have a glass, if it's isotropic.
Right. And watch for dendrites growing in it for more metamorphism.
Exactly. Yeah, you can look for that too. Yeah.
Okay, looks like we're just finishing up our spectrum number 35.
So what I can do is let me check the, let's see. So the first point we got was this high calcium pyroxene. So we can see it's that. Let's check really quick. Just want to check these olivines. So this is an olivine that's in the vein. This is this one right here. And let's compare it to one that's outside of the vein. So let's compare it to spectrum 31. So I'm going to toggle between the spectra and we'll see if there's any noticeable differences.
Okay.
So let's see. So looks like the iron goes up outside of the vein a little bit.
Yeah.
But we can double check that here.
Yeah, but the ratios of magnesium and
yes, so let's see. So okay, so I just compare these really quick. So if you want, we can just quickly calculate the phthalate values of these. So this is in the vein. So that would be, let's see, 6.72 divided by, what would that be? Let's see, is that 28 point, is that 44? Something like that?
Okay.
Okay, so we get a phthalate value of about 23.6. And then let's do the one that's in the host. So 7.31 divided by 28 point, sorry, 28.46. And we get a value of about 25.6. So we do see there is a compositional change.
right.
So what this tells us is that this olivine grain likely wasn't trained in the melt and may have undergone some chemical exchange with the melt while hot. So elements like iron and magnesium may have been redistributed or migrated. And it looks to me like you can see there's a little more green towards this melt. So it looks to me like some magnesium was coming in, and what that results in is a lower phthalate value.
Right.
So yeah, so spectrum 29, if I look at 30, I probably may expect a similar value. Well, actually 30 looks okay. 30 looks like the same outside the vein. So it looks like it was just this class, right, this olivine grain right here that got affected by this melt process and not this one.
So it might have stayed hotter for a little longer and allow that elemental exchange.
Yeah, could have definitely been that. This is a 2D section of a 3D grain we're looking at, so maybe the morphology of these grains are different. So that definitely can control. But yeah, you can definitely see that in the shock vein, it has altered the composition of these olivines. So really cool.
Cool. Thank you, Daniel.
Yeah, no problem, Pat. All right, so where shall we go next?
Chris, do you have a spot picked out?
No, I don't. I mean, I've just been kind of enjoying other people, and if there's something Daniel finds particularly interesting, I'm open to that. I don't have a spot picked out.
Okay.
Okay, I do. This is David. I do.
Go for it.
Okay, and so I am the light green. It's there's a vein, and above it is two kind of cool looking chondrules.
Okay.
thought that would be interesting, especially, and again, I may choose something in one of those chondrules, and the rest I think I'm going to leave up to you for time,
Sure, sure.
because I'm fascinated by what you're doing.
No problem. So that's actually great because we're near one of those chondrules right now. So let me navigate to that.
Because they actually look in really good shape too, which is, you know, sometimes you do see in
Yeah. So I believe that there are two chondrules here that so the one that's upper left of the light green will be this one. And then probably the other one, let's see, I think let's see. Oh, actually, sorry, I stand corrected. So this, let's see, that's the vein running that way. Okay, yeah, so this looks like one of the chondrules here, and then we have this, I think this is a pretty large one actually, right here. Yeah.
Oh, yeah.
So if you want, we can go in this one. Let's see if there's any others there nearby. Maybe, oh yeah, we have a concentric chondrule right here. Oh, these are actually very interesting.
Yeah, I was thinking that those might be really interesting because from what I saw, there's a lot of recrystallized chondrules, but these look really kind of interesting.
All right, let's check it out. I've actually seen very little of these concentrically zoned chondrules, so this is actually something very interesting to me too. So for anyone who's seen a chondrule in a chondrule, this is kind of what we're looking at here.
Chondruleception.
For me, it just looked kind of interesting, and you had an actual term for it, so that's great.
Some people call them compound chondrules, concentric chondrules. It depends on the literature, but yeah, there's been a lot of research done by this. Dr. Alan Rubin, who has talked quite a bit on Knowledge Bolide, he's published quite a number of papers on interesting concentrically zoned chondrules and how they form. So let me see if I can get a mix of this inner part and this outer shell somewhere here, so we can get a mix of them.
I mean, that looked like a shielded chondrule to me, but again, all
right,
I'm not quite sure what I'm looking at. But
so we're at the bottom of this chondrule, but we're getting all right, let me share my screen now. Okay, and we're getting the interior part. So we're getting a mix of the inner chondrule, looks to be a coarse shell and another coarse shell. So this may be maybe like a three generation chondrule, maybe two, something like that. But it's definitely seen quite a bit. It's at least two distinct events to form this object. So that's really cool.
Does that tell you anything, or is that just luck of the draw?
Well, you have to form the inside shell first. Then you can either have a very thick igneous rim around that chondrule, or you have a second event where you melt the outside, or you add on material and then you form that, and then you have a later event that adds on more material. What I would expect is, because this meteorite has been heavily metamorphosed, the composition of the inside and the outside and everything else should be equilibrated. So you kind of lose a lot of information as to the history, but you can at least still texturally see it a little bit.
And would that also talk to the high shock level? Perhaps.
Hard to say. I mean, you could look at, fractures that maybe run across this sample and sort of try to determine like when the shock event took place, but this chondrule, formed and entered this meteorite likely before that shock event took place.
Gotcha.
Yeah. So I'm just removing. Sometimes when you do maps, it includes elements like bromine and some other elements we don't want. So I'm just removing it, but just let that load, and then we'll find a couple spots to get.
Well, this really did demonstrate how looking at it visually and looking through the electron microscope are just so different.
Yeah.
Yeah, it's really.
Mm. Well, what's amazing is I look at it as an untrained person. I look at it as very cool art. You can zoom in, and it's almost almost fractal. It just keeps going,
No.
but you don't get lost on the little splash of orange. Yeah, it's cool and all. It tells you something, but like what? Let's get down to the meat and nuts here. We got to go like this grain versus the grain. Yeah, I could see many hours, expensive hours wasted.
This
Oh,
is
I would.
this is where we need to crowdfund Marissa some time on the electron microscope.
Yeah.
Yeah. She won't have to stack anything, that's for sure.
There's oftentimes some competitions that companies like Oxford Instruments or like Zeiss, they have like send your coolest photo of something, using one of these things. So I've submitted a few things of like Condrules or something. I never won anything because usually the people who win are like they have like nanoparticles of some, unique contamination product on like a semiconductor chip, and they're like very tiny objects. But meteorites are cool too. But,
Yeah.
yeah.
Wow. Oh, this
Wow. What's happening there?
that red. That's, I guess, calcium.
Topher, I'm glad you don't own one of these because if you were sitting at it for hours, you'd be complaining about your neck and your back.
Oh, I would have a virtual reality setup. I'd be in goggles in my chair, just turning into.
Oh, great! Just like Honey, I Shrunk the Kids.
Topher, if you can't keep the SEM at home, I have a van that'll fit in.
Some great ideas for the next calendar.
Yeah.
Okay. All right. So we're all set for some spots. So we can take a few olivines. We can do them here and here, and a few low-cast empiric sands.
Let's see. Yeah, I would say for like one of each area and see what's going on.
Sure, we can do that. So let me grab. Let's go somewhere in the center of this.
That looks clean.
Condrule. We can try maybe this rim here. See if it's the same. And then we can sort of move out to this like outer shell here. I don't know if you prefer left side or right side or center.
They all look similar. I just the cleanest, without cracks.
All right, let's try here. Okay, so we got 3 more olivines. That's pretty good. And now for the pyroxenes, same thing. So we can find. So we definitely don't want to go here, right? This is a contamination spot.
That's contamination.
So maybe somewhere here.
There's some right about in that area is really clean.
Yeah, yeah. So yeah, once you see the grayscale and your eye gets trained right away, it's so easy to like catch on and know like where to get spots. Once you train your eye, yeah.
Absolutely. I mean, there's areas, and you get it, zoom in a little bit, and you can really see where it really is clean.
Yep.
Now, those dark areas, what are those?
These?
Yeah, no, the dark cracks.
Oh, these right here?
Yeah.
They're just cracks, in the sample.
Okay.
Because there's no signal that you can get from here, that's usually indicative that you have a crack.
Oh, okay.
Yeah.
Okay, that's good. That answers that. And then like I said, I'll leave it to you to where you think is best.
I've actually learned. I mean, I'm learning a lot, but one thing I learned, like, I can't believe when you look back like 20 minutes ago, what an idiot I was. I'm looking at it as going, I want the most colorful palette in the world. Zoom in on something that has like just a palette, a spray of everything.
Yes, me too. Guilty as charged.
Yeah, rather than go for the biggest plate without any cracks, solid color.
I know.
So this blue thing right here, this looks like contamination material as well. So especially whenever you see a crack and you see something in the crack, it could be a powder, it could be a grain of sand, it could be something in there. So this is contamination. But you can see it's rich in aluminum, which is pretty typical in ordinary chondrites. You tend to get some aluminum-rich contamination products.
Hmm. Is that weathering or?
Could be. Sometimes during sample preparation, if you're trying to get rid of a carbon coat, you use
Oh,
alumina like
yeah.
a slurry to remove it, and you can get stuff embedded. I don't think they use it. They might in the thin section making process use something that maybe had this alumina powder potentially, but something that's pretty typical weathering would be this. So this is a, let's see, looks like a, could be a metal or troilite grain, but you can see this sort of, this is oxidation. So this is
Oh.
weathering right here. You can see it change the color. You can see it's no longer bright and shiny. It's all kind of messed up. This is what weathering does.
Oh,
Yeah.
I see. No,
Wow.
that's good. That's very helpful. Yeah.
Yeah. If you see other signs of weathering that's not chemical, I would love to see it as well.
Yeah, here too. You can see weathering veins, and you can see this weathering vein that propagates from this grain. So what likely happened was that this grain was here. During shock heating, you melted part of it. It went in through these fractures. And then later over time, these fractures were weathered while sitting on Earth. And so now they've turned into weathering veins. But they were where pre-existing fractures were in the rock. Yeah.
Now, do you use that information when you determine what weathering number to give it?
Sometimes, mostly what I do for weathering grade is I tend to look at the fin section, and I tend to look at it in reflected light, which is where you can see the opaques like metal and sulfide pop out. And I tend to see what percentage of those are weathered relative to like all of the grains. And then, I give like a W2, W3 for assessment. Yeah.
Okay.
There's different ways. Some people just look at the hand specimen and they're like, oh, this is a mild weathering, moderate weathering, or heavy weathering. It depends what system you use. I tend to just use a mix.
Yeah, that sounded like the way I do it. When I'm at Tucson, that's a real good method for me.
Yeah. When we classify, we tend to say weathering grade and shock stage are normally most of the time ±1. Sometimes. So if you see a weather W2 and then you look at a piece and it's like super weathered, and then you see another sample, it's like W3 and it doesn't look as weathered. It's generally speaking not always perfect. Like ±1. Yeah. Okay.
Out of curiosity, when you're doing all of this classification on these really fine, small areas, what, if any, of your classification information is gleaned from the main mass photos? Like, do you ever zoom back mentally and look at the entire rock and go, well, now I understand what I'm seeing even better?
All the time. I can't stress enough. It's so important to see nice photos of the main mass piece, especially slices, because thin sections are just small bits from that rock that get turned into these that we used to study. But this could have been taken from one part of the rock that's completely different from everything else. So especially with breccias like HEDs, I always look at the main mass and I try to make sure that like the percentage of eucrites and diogenites in this material I'm sampling, is it the same as the main mass? Is it different? It's important because if somebody wanted to do research on the sample and the thin section I took was from a piece that's not representative of everything, they might get a false interpretation. So like a great example of that, Erichidia 004 has distinct, high metal, low metal lithologies. Sometimes you find both together. So if you send a piece of the high metal in and I get it classified, and then someone wants to do research on the low metal piece, they might not have that. So it's important to get a representative piece from the whole rock, if you can, when you send in for classification work.
Perfect. Thank you.
Yeah. Okay, so we're on to site number 6. So yes. So Marissa, do you happen to have any sites of interest? Because I know you told me that you were interested in some of these.
The spot I picked was the light blue spot.
Light blue. Okay. All right. So that is towards the bottom. Okay, that's good. So that means we're getting a pretty good sampling of different areas of the sample. Okay. All right, so let me navigate there. So yeah, one of the important things when you're classifying is you want to try to spread out as much as you can on the thin section. So going to different areas and is good. So let me, all right, so let's navigate there. So what I'll do is I'm gonna go to, let's see, bottom left, and then I'll try to go somewhere in the middle, and then we'll just see if there's anything interesting there. If you see anything interesting, just tell me to stop and we can just get stuff right away. So I'll go a little, let me just zoom up a little bit here. And then if you see anything here that's interesting you, just let me know and I'll stop. All right, so I think we're getting to the edge. So there's this big Condrule that is, I think, right before the edge. Let's see, I think so. Oh, no, it's
Yeah,
actually,
that area looks pretty cool.
sure. So let's see. Okay, so we've got a few Condrules. We got this big Condrule here, the smaller one here. We've got a lot of host the matrix. Do you want to get like somewhere in the middle? Do you want to go more just on the Condrule or here? Or what's your preference?
Like somewhere like in the middle, so there's some of the Condrule and some of the matrix.
Sure. All right, so let's go somewhere here, and then we'll try to see if we can get everything in focus. One of the coolest, or I guess one of the trickiest parts is when you come to a very cool area and then you're trying to see how much of it you can get while like being zoomed in enough. So let me see if I can do that. Maybe 300x might be good. Yeah, something there. All right, so then, sorry about that. Let me get this in focus. And then let me go back to 300x. Let's see, right around there. Let's get that somewhere there. Okay, and then let me share my screen and we'll start the image.
My whole thought process was trying to pick like any weird inclusion I could find that maybe was a messed up Condrule, or because but going from inclusion to Condrule is so tricky to tell the difference.
Yeah, I 100% agree. One of the things that I find interesting when looking at some type 3 chondrites are these igneous inclusions. My advisor, Alex, has done a lot of work looking at igneous inclusions in ordinary chondrites that could be from some planetesimal, and they're different from chondrules. And, one of the ways you can spot them is by differences in chemistry. Now, we might not see it on here because the sample has been equilibrated, but for all we know, the texture of, this object may be different from that of a typical chondrule. But either way, it's still, is cool to just sample it and see if there's anything potentially unusual about it. So we can definitely take a look at this object, the bottom of this chondrule, and then everything else here.
You know, I think the only question I could think of for you is like, have you ever found a mineral that caught you off guard and you were like, whoa, wow, wasn't expecting that?
Yeah, I mean, I get quite a bit of those. Probably the most notable one would be the the pink spinel anorthosite rock that I found in this interesting lunar meteorite that Craig Lehman sent to me. Spinel is what we call an accessory mineral phase that you tend to find in igneous rocks on Earth. Maybe makes up 1% at the most. And so finding a rock that has 50%, 40 to 50% spinel, it just it's really unheard of in any kind of geologic scenario. And so on the moon, we knew that there was a rock type that was rich in spinel because we had spacecraft orbiting the moon that used UV, visible and near infrared, spectroscopy to sort of map the composition of the surface of the moon just to see if it's the same or different. And they found there was an anomalous areas that were just had this rock that just had a ton of spinel in it, but we didn't have any of it in our sample collection, either from Apollo or from Luna or from the Chang'e, 4, 5, 6 samples. But I found this rock in a lunar meteorite, and from finding it, we were able to do chemical composition work like what we're doing now on this sample, and we were able to match the data that we found that fit perfectly with this model that explained how that rock formed. So there were different models to explain how you form a rock rich in spinel, and our mineral chemistry fit with one model very well. So the paper that we had published says that that rock type that we found likely formed from this particular model. And so from that point, that's been a major point of my dissertation work with lunar meteorites, is working on these unusual spinel-rich rocks that I found. And there's another lunar meteorite that I've found them in as well, and I'm currently writing a second paper on that one. But I found some other weird minerals that you would never find, like this one called cordierite, which is, normally also an accessory mineral you find in metamorphic rocks on Earth, but I'm finding it everywhere in this rock. So yeah, so stay tuned. There's another paper coming out on that. Hopefully in a few months I'll have it submitted. So yeah, but that's the most recent example of that. Okay, so are there any spots that interest you, Marissa? So we have olivines up here. We have some here. We have some here. We have these small ones, but we have some larger areas here. And then for the pyroxenes, we have a lot of these low calcium pyroxenes kind of everywhere. So if there's any spots that interest you.
Sure, you could pick from that larger area anywhere on olivine up there.
Okay, let's see. Let me get this second image here. So let's get probably here. And then let's see. So I probably want to see this middle area here just to make sure it's the same. And then is there any last area for olivine you're interested in? Anywhere down here?
Yeah, I was thinking the bottom.
Sure. We got this grain here on the left or this grain on the right?
Maybe on the right if we can get that little guy.
Sure. Let's see. So let me just make sure that we're within 1 micron in size. Oh yeah, so this is 25 microns. So if I go here, we're pretty safe. I'll go right there. All right, and then we have some low calcium pyroxenes we have to get. So I'll grab one somewhere here just so we have one here, but let's see there. But do you have, let's see, so from somewhere in the middle, is there anywhere here that might interest you for a low calcium pyroxene?
Yeah, right near that metallic grain would be perfect.
Sure. All right, so let's see. So I'll go to the left of this troilite, so right there. And then let's see, for the final one, do you want to go somewhere up here or do you want to go somewhere down here?
You can pick anywhere.
All right, let's see. So let me check both areas out. Let's see this one. So I kind of like this area a little better just because there's less of that some contamination I saw down there. All right. Cool. All right, so we got a couple spots, and I could just very briefly just check the olivine composition, and it looks pretty similar to the other points. So similar phalite values I would expect. So also consistent with a equilibrated sample. While those pyroxenes are finishing up, we can look at the feldspar grain size, and we can see it's kind of variable, right? Like you see it's coarse over here, it's pretty big, and then it gets kind of small over here. This can happen sometimes, especially, during the fact that whenever you have heating, right, you have different phases that are essentially against each other. So essentially how these things heat up is primarily through conduction. So, if temperature isn't consistent across the entire sample, that like you have a thermal gradient, you're not going to grow all the feldspar to the same size in the same amount of time. Also, if you have something like a really big chondrule that has very small feldspar to begin with versus another area that maybe has larger feldspar, you're giving more opportunities for this to grow versus this, where you have to get these smaller, grains to kind of nucleate and grow and then sort of merge together, which takes a little bit more time than something like this that already was large. So that probably can explain why it's variable, but you can see like determining whether this is a type 5 or a type 6, we can't do that from this one area. So that's why all those other areas we got previously, like they help with, evaluating this to that extent. So
Very cool. Thank you, Daniel.
yeah, no problem. No problem. All right. I'll just quickly check this. So yeah, the low calcium pyroxene, it's pretty much consistent with what we saw before. So yeah, so that's pretty cool. All right. Yeah,
If anyone else has any questions or something, please drop them into the chat. If you are a paid member of group classification 1 and you would like to at least pinpoint an area, maybe not go through the entire thing, but just pinpoint an area, at least let us know, jump in the chat. Daniel?
Yeah. So my iPad's got about, let's see, I think 17%. So I can do one more site before my iPad goes out.
Well, the site I chose was the darker green. It looked like a reasonably well preserved chondrule. So I guess my question is, how many chondrules do you like to survey? How many is enough? Do you do 1? Do you do 5? Do you do 10 on a typical ordinary chondrite?
So it again all depends on whether I'm looking at a type 6 versus a type 3. On a type 3, I have to look at a lot of chondrules, so between 20 and 30. On a type 6, I normally look at matrix and some of the chondrules, but I don't normally look at like a certain number. It's just to establish whether or not the sample is like homogeneous or different.
Okay. Well, I'm happy to go to the green or to give up my spot in the interest of time, whichever Daniel prefers.
Ooh. Oh, yeah.
What color is Cal's? And maybe we'll just let Daniel choose between them and let us know like why he would pick one over the other.
Yeah, mine is orange.
Oh, they're very close.
Okay, well, I can go in between. How about that? I
Let's
can
see,
find somewhere in between that maybe samples a bit of what you both are looking for.
We go a little bit closer to Cal because he actually supports us on Patreon.
Actually, the
Favoritism.
orange one covers up 2 large grains that abut, and so I was wondering if they were both the same stuff.
All right, let's see. So, okay, let me see if I can navigate where we are here. All right, so I think yeah, okay, so right here is where that point was. So let me go a little more this way, and then let me see if I can find it. So next time I do this, I have to, there's a setting where you can fix a thin section, like a picture, to sample coordinates, if you can find them, and then it kind of lets you navigate through while point and click. So next time we do this, I will have that set up, so it'll be a little faster.
I absolutely love hearing that. There will be a next time. Please and thank you.
Okay, so let me see. So that would be there. Okay, okay, I think I know where we are now. So we're there. And then if I just go down from here, yep. Okay, so there's that grain there. And then this should be where the green is. Yep, I think that's this right here. And then the orange is going to be diagonally down this way. And I think it's this object right here. So it looks like, wow, yeah, we have like 5 chondrules, pretty big chondrules that we can see here. So I'll let everyone decide where we want to sample in here. We can choose between somewhere in the middle here. We can go here.
Don't get
we
quiet,
can go here.
Cal.
Somewhere in the middle.
Somewhere in the middle?
Sounds
Yeah.
good.
Okay. All right. So let's see. So if I had to choose, let's go.
Yeah, dealer's choice in this one, right?
Let's see. So maybe we get a little bit of that shock melt too. So might as well we're getting a little bit of everything here. All right. So let's go there. We do this. I get to 250. All right. Something like that. Okay. And then let me just focus.
Yeah, I have a quick question. I think before Daniel logged in, I mentioned that I would run a poll at the end of the Hangout to see what everybody guesses for the classification. Does that make sense? Like, is it already obvious to everybody, or like, do you know the exact classification, Daniel, or like, do you need to do work still?
I'm between L5 and L6 personally. I'm leaning towards L6, but I have to check all the sites to see if my average feldspar grain size is over 50. But yeah, I'm probably leaning more L6 to L5, but it's one of those two.
Okay.
Yeah.
I'll give you $1.50 if you make it an L6 so I can beat Pat. You know, for science.
Yeah, I'm good with that. It's all good.
So how do you put a weathering grade on it?
You mean what I would assign to it, or?
Well, yeah, is it literally just what we've seen tonight, or is there other things like, I mean, you've seen the main mass pictures, like is there any other data points or any other things that you need or use to assess your, because I would think that the weathering grade is more, it's a sliding scale, more ambiguous than the petrologic grade. So you have what's your criteria?
Yeah, it's a little more ambiguous. I mean, because you can have pieces of the main mass that were more susceptible to alteration and then some that weren't, if there were no fractures that let in, things like water and so forth. So, yeah, I just look at that big slice you sent me, and I look at the thin section and I try to see okay, do I have, most of my metal weathered? Is some of it still good? And then I generally assign the weathering grade. So yeah, I mean, I'd have to relook at it. I think I was either W3 or 4 from what I was looking at. W3 means I think greater than 60%, less than 90, and W4 is 100%. But it's more to W3, I think. It might even be maybe W2. I have to check, but it's somewhere intermediate because I do see some clean metal like here, but then you have this weathered mess of metal right there. So yeah,
Don't
it seems like it's
about my meteorite. It's not a mess. Okay, thanks.
It's an interesting assemblage of iron hydroxides that have replaced primary metal. How about that?
There you go.
So how much correlation would there be between two different classifiers if there's sometimes a bit of a judgment call, whether it's a W3 or 4 or 2? And
Great question. Yeah.
Has that study been done?
I don't. I maybe not with simple ordinary chondrites. I mean, I can definitely. I definitely would probably predict that if you gave the same rock to 4 different classifiers, the thing that would probably be the thing that could change the most would be the weathering grade. The second probably would be the shock stage. The petrologic type is relatively easy to distinguish, using existing schemes. But for weathering grade, it is very subjective. And depending on who you ask, some people, like I said, do different ways of assessing it. So I wouldn't be surprised if someone says W2, someone says W4. somewhere in that ballpark. I don't think there's a perfect answer just because, you'd have to look at the entire main mass and like really try to, narrow it down. So it does depend. What is probably, very important that, you want to make sure is consistent between classifiers is just the classification. So, if someone says this is an H and someone says this is an L, I mean, that's clearly like a big difference right there that needs to be assessed. But if it's something like someone says L5, average grain size was 40 microns of my feldspar, and someone says L6 average grain size was 52 microns of my feldspar. In that case, because it's on such a boundary difference, that's the subjectiveness, I think, right there. Because it also depends on what sites you looked at. Like from the sites we looked at, there could have been other sites that either had larger feldspar or smaller feldspar. So when I do my average, if my average is close to that 50 micron threshold, I could go either way. So that's where that subjectivity comes into place.
Right.
Yeah. So there's always going to be a little bit of subjectivity, no matter what. There's going to be some differences, but the overall L group, highly equilibrated meteorite, that will be consistent, I would expect, between different people.
Great. Thank you.
Unless you just classify fresh witness falls, then it's a weather grade 0. No arguments.
Well, there's like 0.0 for pre-rain and 0.1 for the 1 day of rain, ...
Look at that, how fine those little particles are in the very north from center. Yeah, it looks like a big city map at night.
Let's see what this is. So we got these are troilites. These are essentially troilite blebs that essentially were melted and then they crystallized. So you can see we got troilite in here. Let's see if we can find any. I don't think we can find any metal. I mean, you can see it's all kind of the same color. There is a big metal grain here, so we can take a look at that. Want to see it? Maybe just that. You can see we got metal. There's a little bit of nickel in there. Just to show you what happens if we look at a weathered metal, what that would do, I'm just going to hover over it. So just pay attention to this metal and then watch what happens when I hit this. Okay. So first off, I have some contamination from the outside silicates. So let me find a better spot. 1 second. Okay, let me try here. This probably is better. All right. Okay, so what you'll notice is when I compare this metal to this metal, you'll see that my iron is kind of dropped. It shows sulfur goes up. I think this might be a mix between metal and sulfide, but what I would expect is my overall, I see chlorine in there. This is clearly an alteration product. And I probably would expect my totals to be a lot lower for this than this, because whenever you have iron hydroxides, you incorporate the hydroxyl ion into the structure, and you can't detect hydrogen with EDS, so it'll just give me a lower total. Yeah.
Daniel, if I'm the dumb one asking this question and everyone knows the answer, awesome. Why are there 2 instances of everything? Like there's 2 instances of Fe, Ni. Are those different phases?
Great question. So there's different energy peaks. So when you do, the typical, essentially the way this works is when you have electrons that, essentially the electrons from the scanning electron microscope interacts with atoms in your sample. Sometimes they knock off inner orbital electrons from your samples. And so what that happens is electrons from higher energy orbital shells will fill in the void, to maintain equilibrium. And when that happens, it releases X-rays. Depending on which electron you've knocked off from which orbital in your sample and what electron from the other orbital shell goes in to replace it, it releases a distinctly different, what we call characteristic X-ray. And so when this detector picks up all these X-rays, it's saying that some of my characteristic X-rays for iron will have energies that plot here. These are called the K lines. So K alpha, K beta is there. And then you have some that are here. I don't know if this is L or M. I always forget which one, but this is another energy peak for iron, or you would expect to find it. Mostly when we do EDS, we just care about these K alpha and K beta peaks just because they're easy to detect at the conditions we use. And, you tend to get a decent amount of intensities of them to convert to signal, which you can then convert to chemical composition. Some of these like other lines, like this iron kind of intercepts with this oxygen, or like this, these other peaks there. So yeah, electron, this is a X-ray spectroscopy 101. Yeah, but there's some good books. If you want to read up on scanning electron microscopy, there's a really good book by Reed. It's from 2005, and it's called, I think it's Introduction to Scanning Electron Microscopy, and it teaches you everything from the fundamentals of understanding, the SEM, to understanding these X-ray interactions, to understanding what this all means. It's a really good book, and highly recommend it.
Awesome.
All right, so let me just grab, let's see, just grab another pyroxene here. And then, all right, so we have room for one more olivine and one more pyroxene, so I'll let the group decide for our last 2 points. Where should we get an olivine? Just turn that off. So I need the bright green, and where should we get a low calcium pyroxene, which will be the green-brown color. So we can only get one of each.
I will speak up for the green-brown one. Right above the 62 in spectrum 62, there seems to be a good area.
Okay, so somewhere here?
Yeah.
Okay, so that will give us the olivine. So this is an olivine. Let me try, where's the other map here? Let's go somewhere there. All right, so for the pyroxene, looks like we maybe should sample somewhere in here. So if anyone has any preference.
Just something that looks good.
Something that looks good, okay. Let's see, so we have a clean area right here. So let's grab that. All right, so we got 64 points. Probably about, from there, I'd say maybe about 40 to 50 of them are olivines and pyroxenes that we can use for the analysis. So roughly 20 of each, I'd probably say we got. So that's pretty good. And that's definitely enough for the classification. So great job, everyone. You did
Very
pretty good.
cool. Very cool.
Thank you.
Awesome work, Daniel. Thank you so much.
Oops.
Yeah, no problem. No problem. Let's see. If you want, we could do for this sample, because I went through the explanation of data acquiring. If you wanted to do a session dedicated towards processing and submitting the form, we could do that. And I can hold off on processing this sample. And then during a Hangout, we can show, like, now that we've acquired the data, how do we turn this into an Excel spreadsheet? If that's something that might be of interest. If not, then
I think it would be with this group.
Yeah, knowing these nerds.
Yeah.
No, honestly, I like going through the entire process.
Yeah.
Like we got to this end here, and I've been going hard since 9 this morning, but like my brain's tired, but I don't want to stop. I want to go through, and it's like, okay, yeah, we have this data, but what do we do with it? So that's going to be part 2. That's
part 2. All right. So we will. So part 1 is data collection, and as soon as it stops, we'll stop right there, and then part 2 we'll pick up at another time, and yeah, we'll go through everything from how we process the data, how we ensure we have clean data, which you kind of saw. We were choosing good spots, but also I was looking at the chemistry, and then we'll submit the form at the end.
I'll put the call to action out there right now. If you guys are alive, subscribe to his YouTube channel. If you are a rock hounder and have a sample you think may be a meteorite, especially one that you think may be a lunar meteorite, you can send it to Daniel at.
My email address. Okay, so that will be Daniel Sheikh, so DanielSheikh 68 at gmail.com.
Awesome. And I will also put that in the comments or the description to this video. So there you go. You put 3 hours into science, and you got not only something that you don't ever see, a classification done live, but you have now access to get your sample in front of Daniel. If your sample doesn't look like a meteorite to him, he probably will not reply. Just telling you. But if it is a meteoritic or he thinks it's worthy of it, you will get a reply. You don't need to pound his email. Okay? Go to his channel, subscribe, send your samples to Daniel. And if this is the kind of education and entertainment you like and you realize you can't get it anywhere else, we would really appreciate you subscribing to our channel. But think about a Patreon or YouTube membership. Patreon membership is better. You can join for $10. You can join for free, but you get member access at $10 a month, and it just goes from there. So thank you very much to our esteemed crew member, Daniel Sheikh, classifier to the stars.
Can I read a chat message before you close it off?
Please, yes.
I just thought it was really nice. It is from, let me scroll back up, from Jeff Gerber. It says, thank you so much. Thank you all so much for doing this. Especially thank you to Cal for telling me about it. Thank you to Pat for answering so many questions in the chat. And he's been completely fascinated for 3.5 hours.
That is
another nerd.
And
Awesome.
wow,
Thank you. Thank you very much.
It would have been easy to keep viewers for 3.5 hours if we could have shown your face the whole time, Daniel.
Yeah, I'd probably have to have a third monitor for that. So I'd probably have to. Well, next time at least now I know my iPad for sure, the computer, and then let's see. Yeah, definitely. Maybe I can have my phone as well to show the computer screens or try something with that.
And by all means, you can have a copy of this video for your channel if you want to put it up on your channel as well. It doesn't matter to me, but I just appreciate your partnership, and the crew really does as well, especially when you consider, you know, your love is lunars. You're a classifier, but you love lunars. And yeah, it's a meteorite, but it's an L6. It's a boring meteorite. There's nothing, but the amount of time and energy and heart and brain you put into conversing with us and spending 3 hours rather than just your cursory hour classification really means a lot to us and to our community. So thank you very much, Daniel.
Yeah, not a problem. Thanks for having me. And for anyone who's sent me samples in the past for classification, if you have other samples and you kind of want to do a similar approach to this, if I have a day where I'm classifying and you want to connect via Zoom, we can definitely arrange something like that. And yeah, happy to do more group classifications. I know Vince, he has one coming up, so hopefully he has a similar setup and can do something similar. Maybe I set the bar too high for him.
I know. I was gonna say, how is he gonna do it? But yeah,
I was gonna ask him. I'm like, oh, I don't want to pressure him if he's ready to do this.
Yeah. And this was a master class. There were a whole bunch of really important details that you went over, and thank you for thinking out loud through the process so that we can listen.
And maybe next time we'll know our way around a thin section and give you directions.
Oh, and
All right.
I wanna say thank you very, very much.
Awesome, Jules. Thank you very much. I'm sorry we didn't get a chance to get you get your spots scoped out. But
That's fine. I'm still awake and I'm thrilled. I'm awake, and that was so interesting and I really enjoyed it. Thank you, Daniel. That was awesome. Super awesome. Thank you.
we're gonna get his head so big, guys. We got to shut down the love fest. No, we're really fortunate to have a young classifier who will spend time with the community scientists like ourselves, which means just backyard nobodies. So thank you very much to everyone on the crew. I appreciate you guys being here and being involved in this classification project. There's only more and better things to come. So thanks a lot and have a great week.